We are glad to invite 6 speakers to introduce their influential works and share their perspective thoughts of related topics. At last, we are glad to invite 2 winner teams to share their ideas of solving Zoom and Revere tasks. One team won the first place in both Zoom and Revere, and the other team won the second place in the Zoom challenge. Okay, let's begin. Firstly, we introduce Fengda Zhu from Monash University to share their report of the scenario-oriented object navigation challenge.
Hello everyone, I'm Fengda Zhu from Monash University. Today I'm going to give a summary report for our first scenario-oriented object navigation task. The report is divided into 3 parts. First, I will introduce the scenario-oriented object navigation task. Second, I will analyze the possible difficulties of Zoom task to give a promising directions in solving realistic indoor navigation. At last, I will demonstrate the results of the Zoom challenge. Here I'm going to introduce the scenario-oriented object navigation task. The motivation of this task is to propose a more realistic scenario where a human interacts with a robot. Different from previous vision language navigation tasks, which use a step-by-step instruction to guide an agent from a starting position to a target. The Zoom task focuses on the target only in navigation and try to relieve the dependency between the target description and the step-by-step routing description. As shown in the left side of this figure, an instruction contains thorough descriptions to guide the agent to find a unique object from anywhere in the house. This instruction contains object name, object attribute, object relationship, target area, and neighbor areas. By using this information, an agent is able to localize a unique object from anywhere in a house. Therefore, our dataset have 2 unique features among all vision language navigation tasks: starting independent and target-oriented. The starting independent means the agent is able to navigate starting from anywhere in the house. The target-oriented means the instruction has no assumption of the route how an agent navigates to a target. The agent has to find the target object by a cost-to-find researching, as shown in the right figure. Firstly, it explores the house and finds the areas that our object maybe exists. Then it searches in the candidate areas for the target object by scenario descriptions. Here we demonstrate our data annotation methods. First, we annotate all views of an object in a panoramic space by bounding boxes. If an object can be reached from multiple positions, we will label all bounding boxes of the object from all these views. Secondly, we annotate descriptions of an object by 6 steps. By observing the panoramic scenario, the annotator annotates the object name, object attribute, and the relationships between the target object and the neighbor objects. Then the human annotator navigates in the house and annotates the area where the object locates in, and annotates the descriptions of nearby areas. At last, we rewrite all the information as 2 or 3 natural language sentences. This is the data analysis of the Zoom task. The Zoom task contains 3,800 instructions with a vocabulary of 1,600 words. The average number of the words of instructions is 38.6, which ensures the power of the presentation. The trajectory length ranging from 15 meters to more than 60 meters. Our task provides much more in long-term trajectories, which makes the dataset more challenging. The right figure illustrates the proportion of word numbers in the 4 instruction annotating steps, we can infer that the annotation of all parts are approximately balanced. Here we are going to introduce what makes the zoom task difficult. First, as we discussed above, the natural language description is complex, which is challenging for an agent to correctly comprehend. Secondly, locating a unique object in a house is difficult. Since there are many objects from the same class in a big house, the agent may be confused in selecting two similar objects. Thirdly, to achieve efficient navigation, the agent must learn to cost-to-find searching. It requires diverse skills to accomplish that, including high-level vision language alignment and embodied room structure modeling. Here we introduce the evaluation matrix. We use two main metrics. The SPL is for evaluating the navigation process, and the SFPL is used for evaluating both the navigation and the localization process. SNAV indicates if an agent successfully reached the target, and the SLOC indicates if an agent successfully locates the target. Similar to SPL, the LNAV indicates the actual navigation length, and the LGT indicates the ground truth navigation length. We also have other metrics to describe the performance of an agent, including trajectory length, oracle success rate, and success rate. This is the result of Zoom challenge. 3 teams joined our challenge and they all achieved good performance. We can see the second place team largely improves the localization performance, and the first place team largely improves both the navigation performance and the localization performance. Today, we invite these 2 teams to share their methods of solving the Zoom task. Thank you everyone, this is my report.
Okay. Next, we will introduce Yuan Kaiqi from the University of Adelaide to share their report of the remoted embodied visual referring expression challenge.
Hello everyone, I'm Yuan Kaiqi. I'm glad to give a summary report for our Reverie challenge. My report will start with an introduction of the Reverie task. Then I will present the results of this challenge. Finally, I will briefly summarize existing methods for the Reverie task. First, what is the Reverie task? Reverie is an indoor remote object grounding task. Here is a demo. The robot agent is given a natural language instruction referring to a remote object. The agent must navigate to a suitable location and identify the target object. The agent can look up, look down, and look around at each step. The blue cylinders indicate navigable viewpoints provided by the simulator. Reverie differs from other existing vision language tasks. Compared with the conventional referring expression grounding task, the target in Reverie cannot be seen at the starting location. Compared with the vision language navigation tasks, Reverie uses short, high-level instructions instead of step-by-step ones. The Reverie task is challenging in 3 aspects. First, the object appearance changes greatly in terms of shape, scale, and aspect ratio, leading to difficulties in object recognition. Second, the instructions involve various linguistic phenomena, such as dangling modifiers, spatial relations, and imperatives. This requires the model to have a good ability to understand the complex language. Third, the instructions are very short, and they only describe the target room and target object. So to finish this task, a model needs to learn common knowledge about navigation. Okay, that's about the Revry task. Now let's move on to the results on the challenge. Before that, let's have a look at the two main metrics, RGS and RGS-PL. RGS is the success rate of locating target objects. RGS-PL is the RGS weighted by path length. The longer the path, the smaller the score. Besides the main metrics, we also use an auxiliary metric, navigation success rate, to measure the performance of the navigation subtask. A navigation is considered successful if the target object can be seen at the stop location and within 3 meters. Now let's have a look at the results. This figure shows all the received submissions since the Revry task was proposed, not only the results for this year's challenge. The blue curve is for navigation success rate, the orange curve is for RGS, and the green curve is for RGS-PL. We can see that these three kinds of results are highly related. A higher navigation success rate usually leads to a higher RGS and RGS-PL. The first curve peak is achieved by the challenge winner last year. The following relatively smooth peaks are achieved in several recently published papers. The next peak, also the current best results, is achieved by a rule-based method. But currently, we didn't find any article describing this method. Then we come to the results of this year's Revry challenge. We can see that the performance are very close for most submissions. And the best performance has a significant margin to the runner-up. Let's congratulate the winner team. They will give a technical report later on today's workshop. Finally, I briefly summarize existing techniques. I found 4 published papers working on the Revry task. They all utilize visual-dialog-like models. The difference is that the first 3 methods use pure visual-dialog incorporated temporal context to tackle the Revry task. The last method just uses visual-dialog as an encoder. Besides that, recurrent BERT performs in-domain pre-training. ORIST just fine-tune out-of-domain pre-trained models. AirBERT performs pre-training on self-collected data. And SRA takes advantage of memory augmentation. That's the key points of these papers. For more details, please refer to corresponding papers. That's all. Thanks for your attention.
Okay, thanks Yuan Kaiqi. Now is the question time. Is anybody have questions of the report of Zoom or Revere challenges? Okay. If you have more questions, please email to the authors. Now we are glad to introduce the first speaker, Jonathan Bisk, assistant professor from Carnegie Mellon University, to share.
Hello. Let's see. Sorry, I think everyone else probably recorded. And then so I'm going to be the one person who has to remember how to use Zoom live. So sorry for that, everybody. Let's try. Oops. And how does one swap their screens? There. Cool. All right. Hello, I'm going to be talking about asking questions and following instructions. This is not unrelated to the discussion that we were just having about instruction following and language in general, which I think is sort of going to be a theme of probably most of the talks today. But I'm going to try to put it in a slightly larger context, I think. So in particular, we typically think about this, I think a lot of the people, for example, the speakers and the participants in this workshop think about navigation as sort of an interaction, human interaction modality, because they're thinking, well, there is language coming in. And so that means that like we've got the human in the loop in some sense. And, and that's true, except that what we really also want is to make sure that we have humans that are being communicated with by the agent, not just via their actions. And so we really kind of want to broaden the notion of interaction to dialogue. Even in the context of instruction following, it's clearly the case that if we're just doing navigation, then that's not like that's a trivial task, but it does simplify certain aspects of our world. And so in particular, if we were to add the ability to have articulated objects and so forth, then we end up with a more complicated environment for interaction. And we'll talk a little bit about Alfred in that context. And then I think there's kind of a sort of more general question about how do you then sort of maybe merge those two? And that's, I think, where we probably want to be going as a community. So I'll talk, only mention that very briefly, but that's kind of, I think, where this is all sort of building towards. So the first place I'll start is in talking about dialogue. And this is some work now from, I guess, over a year ago on a recursive mental model for dialogue navigation. And so the context for this is if you think about the kind of standard VLN kind of paradigm that we're familiar with, then the way that typically works is we get some reasonably low level detailed instructions, and then we're supposed to just execute those. But if we actually had two people around, you probably wouldn't give them this incredibly verbose set of instructions that you're going to then sort of execute slowly. Instead, you would probably give them some reasonably high level thing. Like, by the way, our goal is that we're trying to find a mat in this house. And if you know the environment, then you're going to be able to give them, the person who's actually navigating, some amount of help in trying to find this. So here we have a navigator who is going to be in the environment and has access to this mat, to the hint, and they're looking around and trying to see where they are and whether or not they think that they can find this object. And so when they can't find the object, the natural thing is not for them to just start a search policy, but the natural thing for them is to start asking questions, right? So, well, from where I am, should I be going into the hall or into the office? And in this paradigm, this is built off of Jesse Thomason's work from Coral, is that he basically then says, well, the guide is going to have access to the next few steps, sort of has the oracle next few steps of this trajectory. And so they can use that in order to provide an answer. So you need to go left into the hall and follow it to a living room. And so it's, it's kind of like if we were giving sort of customized versions of each of those steps that we're familiar with in a standard navigation task. So now the agent is able to, in this case, the navigator is able to see some additional images based off of the trajectory they've just taken. And then they may ask a follow-up question like, okay, so now should I go upstairs and so forth. And so the goal of this work is that where he collected these dialogues with human-human interaction, we want to be able to replace both of these components, the navigator and the guide, with something, some model, some machine learning model of some kind. And so this poses a few challenges. So in particular, it poses this sort of these two. So we have or these four, excuse me, which are that the navigator needs to decide when to ask a question. So this is a research question in its own right, sort of understanding uncertainty. You need a navigator that can generate questions. And so obviously we have an NLG problem here. We need a guide that can answer questions, another sort of contextualized NLG problem. And then we want a navigator that can take the right actions. And so oftentimes with VLN, we're really only thinking about challenge 4. And in this context, or more generally in dialogue, there's at least these other 3 components. So the environment in which we're going to be working, as I was mentioning, is this is what Jesse Thomason collected. This is built on the same environments. So this is the same sort of Matterport 3D simulator that a lot of VLN style tasks are based off of, except now we have these 2000 human-human dialogues. So a number of trajectories, a number of houses, but the main difference here being the dialogues. And so we're going to have some sort of an agent. They're going to start at some location and they have some sort of a goal. And so in this case, for example, if it says that there's the fire extinguisher is sort of the hint, that's what you're looking for. And so again, if, as is we've sort of discovered from analyzing, we as a community have discovered from analyzing lots of VLN agents, is that the main thing they're really good at is search, right? So they really tend to search the environment, find something that kind of satisfies a stopping criterion, and then stop. And there's been all this work, for instance, I think some of the baby walk work and so forth, to try to kind of get agents to actually pay a little bit closer attention to the instructions that they're being given. And so in this case, they could try to do the same thing, right? So we give them, but it's the sort of fire extinguisher is the goal, but it's pretty minimal. And so we're really trying to assess the entire system. So how well does dialogue work and how well is that able to facilitate the navigation? And so just as with the human before, now we can sort of slightly formalize what this looks like for the agents. So if we have an embodied agent, a navigator in this space, they have some hint, they have a maybe panoramic view of what they can see right now. And importantly, they have a dialogue history. Then they're going to try to take some action in this environment, and that's going to update their state. And in particular, we're going to need to define some sort of reward function because we're going to use sort of RL to train this. And so we're going to use a really simple and straightforward reward here, which is simply goal progress. In other words, is it the case that I am moving towards the goal? If so, you get reward. If I'm moving away from the goal, then I do not. We're going to then also have sort of a questioner module, which also has access to this panoramic view, is able to generate language. And so it's going to have a slightly different sort of action space, right, in that it's going to be producing a question. The guide, who also has access to panoramic views and these 5 steps, is going to provide an answer. And so the really simple thing to do here, which is what we do for now, and I'd be really interested to see kind of future work do something more sophisticated, is that we basically use a standard encoder-decoder framework for the guide. So you can kind of think of this as a modified captioning task. You have one agent that needs to generate a question, and that's effectively a captioning task conditioned on both their dialogue history and what they're seeing. You have a guide, which is effectively a captioning task, which is trying to describe the next 5 steps. And then you have the navigator. It's not quite a captioning task in a couple of very important ways, which I won't go fully into here, but the 2 main things are, one, on the navigator side, this notion of conditioning on uncertainty. So really what you want to be doing is only asking for a question at the right time. We have some work that's in submission that tries to look at this question more formally. How do you sort of know when to ask for information? And then the second part is that you don't want to just give a sort of generic next 5 steps, because if you do that, then you're not actually conditioning on the knowledge of the agent, right? So the basic idea behind what is a good answer is, well, a good answer is something that the navigator actually can use. So that might mean that it answers their question more accurately, or it might be that it simply uses vocabulary that that agent actually understands. And if you don't have the sort of right vocabulary, then that caption may be kind of irrelevant. It doesn't lead us anywhere. But this kind of simple baseline gets us off the ground for now. So it means that you can have one system which is producing these questions, another system which is producing answers. They're both accessing this panoramic world, and they're actually then able to execute actions in this space. And so I'm going to harp for a second on the thing I was saying a second ago. So the really interesting question, I think, here, which is not fully answered by this work by any stretch, but I'd like to at least sort of leave it as the nugget from this paper in your brains, is how is it that you're supposed to basically formulate a sort of good dialogue overall? And the way that we think about it is kind of like a search through the dialogue space. So given that we started at some location, we have a navigator which has some hint, and they can maybe take some initial steps. And then we're going to allow them to basically generate during training, we're going to allow them to generate 3 questions. And so each of those 3 questions can then be passed to some sort of a guide, and the guide can now produce answers. And in particular, we're going to let the guide produce 3 answers. And then we're going to pass this, in this case, 9 possible QA pairs to the navigator, and see which of those helps the navigator make the most progress towards the goal. And the idea here is that if you have a good, so what is a good question? It's one that gets you a good answer. What is a good answer? A good answer is one that gets you something that you can actually utilize. What does it mean to be able to utilize it? It means to be able to make progress towards its goal. So you have this kind of distant reward down at the end. And what we want is for our agent to then be able to basically propagate that backwards. So we want it to be able to take that information from having successfully the one sort of real thing in the environment, which is having actually performed the task. We want it to be able to take that information and basically propagate it back in order to update the kinds of answers that it produces and to update the types of questions that it asks. Now, the reason I said this is cheating is because in this case, we're going to do this sort of using the actual models that are the guide and the navigator. In other words, when you ask a question, you're going to get a reward based off of basically how the guide would have answered it 9 different ways. And in reality, that's not how dialogue works, right? So in reality, the way that it should be is that you, the questioner, should have a mental model of how the guide is going to answer your question, and you should be trying to work against that latent model. And this kind of brings into this kind of theory of mind component, which we also have some work on, but not in the sort of fully navigation setting. But in order to test it, at least in this kind of simplified setting, even though it doesn't sort of have a proper theory of mind, that we are actually seeing some amount of progress, we do some comparisons against kind of a baseline seek-to-seek model and also against a kind of simple data augmentation strategy. So in particular, what you're seeing here is if you allow the agents to ask a bunch of questions, as they progress through asking questions, to what extent are they making progress on their goal? To what extent are they actually moving towards the goal? And I'm going to sort of harp on kind of 2 things here. So we have this baseline seek-to-seek model, which is not particularly strong. So a really simple thing that you might think to do is that rather than using RL here, you say, well, why don't I just go ahead and do kind of a simple data augmentation strategy? This works really well in the speaker follower model for VLN, which is in essence what a lot of the machinery is for this paper. So I'm just going to go ahead and have the agent sort of produce a bunch of kind of QA pairs from its model, and then I'm going to train on those. The thing that we found was that possibly because there are some differences between the standard speaker follower setup and the dialogue setup, is that we kind of have a mode collapse issue. So what ends up happening is that the model gets a bunch of its own output, it takes its own output and starts training on it, and it starts to kind of collapse towards these kind of overly simplified and oftentimes repetitive statements. And There's probably a few reasons for this. Some of them may have to do with sort of better ways of doing inference on our side. But the other part of this is that it's not trivial to figure out how you're supposed to kind of initialize these augmentation strategies. So in the standard speaker follower setting, all you have to do is basically put the agent in a new location and then have it go. But in this case, you need there's two agents that are involved here, and you have to have sort of these hints. You have to sort of make sure that like you're actually giving something that's sort of semantically coherent. And so we didn't have a really good way of sort of producing a larger set of these kinds of initializations. And so what may also be going on here is that what we did was we basically tried to add trajectories from the same starting position rather than covering additional starting positions. And so maybe there's some amount of redundancy that's also being built in there. Anyway, caveats aside, the model that does this kind of reinforcement learning based search does actually improve. And so what you're seeing here in the green line is an overall performance improvement in terms of goal progress over the course of a dialogue. Note that we're nowhere near solving this. So we still have quite a ways to go, but we do see that there's a noticeable gap. And also we're seeing this kind of leveling off. So at a certain point, the agent sort of needs some help. To put this all a little bit more sort of quantitatively in a table for you, what this looks like is the following. So these numbers are very low, but this is in terms of goal progress rather than sort of percentage progress, which is what the previous plot was. So this is in terms of meters. And so if you knew the shortest path to get somewhere, in general, you'd be you'd travel about 29 meters. What we're seeing is that our agents, if you allow them just to do search, actually are the best, which is kind of similar to what we saw before, but are able to make more progress in general than their counterparts that are either using only a beam of one or just using sequence-to-sequence data augmentation. In other words, what's happening here is that the models that are tasked with only learning to do search can do a little bit better, but the second that you introduce dialogue, things start to fall apart. So these models are not necessarily very good at being able to handle that dialogue history, and in fact, it's detrimental in general. So to give you a slightly more qualitative sense of what this looks like, here a human dialogue, a sort of collapsed data augmentation, and then what we're seeing from our model. And so here you have this really obvious error case in the data augmentation. Should I go into the room? You are in the goal room. You are in the goal room. These kinds of, even whether or not it's true, but just sort of repeating themselves. And then what we're seeing for the RMM model is a little bit more natural. So should I head forward or bedroom the next hallway in front of me? Not quite, but at least sort of progress. Should I turn left here? And then similarly, the agent is producing the guide agent is producing quite a bit more detailed answers on the other side. Again, not fluent. And if you use something like Blue Score here, you're going to have all kinds of issues in terms of both in terms of low performance and because it's kind of the wrong metric for guaranteeing semantics. So this is kind of where we our head was in terms of trying to start with dialogue and incorporating that into sort of a navigation style setting. And there's a number of places that I think are really interesting to go from here that I'm not going to dive into today. I've already mentioned theory of mind is sort of critical. So you really want to move away from the scenario where you have access to sort of a ground truth guide of any kind. And then the second part is basically this question of uncertainty. So when are you sort of doing information gathering? When's the right time to do additional information gathering and so forth? And so hopefully we'll have some papers, maybe even just on archive on that very soon. So I want to now sort of take the other branch for a second. So I want to talk briefly about Alfred. So Alfred is some work of ours where we say, so now we're not having that complexity of dialogue, but we are having complexity in terms of more interaction in the environment. And so this is basically a setup inside of AI2 Thor rather than inside of the Matterport scans, where you have a high level goal instruction. We also then provide lower level detailed language, very similar to the navigation task, except that in this now rendered instead of real images, but in this sort of rendered scenes, you now can actually take an object, you can move it around, you can open things and close things and so forth. And so this presents a whole bunch of new challenges. And so very quickly, the basic layout of this work is that we basically say, what are the sort of kind of core things that we assume that you are definitely going to need if you are, building an embodied agent? These are not robots, obviously. Anything in VLN, anything in Alfred, these are not robots, but they are sort of at least embodied agents. And so one thing that we have is something like pick and place. We have the need to maybe move more than one object. We have stacking. We have examining in the light. So you're sort of looking at something a little more closely. And then we have, really importantly, this notion of heating, cooling, and washing or rinsing. These are a different category because while all of these require changes to the object's location, orientations, other things like this, that they do have interaction, these final set are immutable or might be immutable. So if you've heated something, like if you cook something, you can't uncook it, things of this nature. And so what we then do is we take these high-level 7 goals and we say, like, let's take the environment and render out a bunch of configurations. In other words, if we have in this case, stacking a fork and a cup on a specific countertop, then what we can do is that we can turn that into a PDDL plan, which we can then render in the environment, have an agent actually execute it. And then we can show that video step by step to humans and ask them sort of how they would have instructed an agent to perform this. And since we can randomly initialize the locations of various objects in the scene, we can do this a couple more times. So we can basically say, actually just go ahead and execute that same exact high-level goal in the same exact room, but with very different low-level plans. So what we end up with is this sort of sampling procedure, executing, and then annotating. So we end up with 3 different ways that you can perform the same high-level task, 9 different language instructions for it. And so I said that we provide low-level language as well. And so here's kind of an example of what that looks like. So given that you have a bunch of these kinds of configurations, which you're seeing at the top for each of these 7 tasks, then you can have these lower-level ones. So in this case, we have put a clean sponge on a metal rack, place a clean sponge on the drying rack. These are the high level. These should be in agreement across all 3 trajectories, all 9 annotations. And then we have these much more concrete things like go to the left, face the faucet, side of the bathtub, things that are low level kind of orientation and interaction kinds of things, closer to what we are accustomed to in a navigation setting. Okay, so why do we introduce this task at all, given that we have these other tasks that we've already been working on? And so I want to talk about the pros and the sort of TBDs on this data. So the nice thing about it is longer horizon plans. So as compared to things like touchdown, virtual home, or room to room, the number of steps required to complete an actual demonstration are substantially higher. So this is the first place, so that we really want to be able to have systems which are able to perform these tasks, even if it requires memory and other kinds of components like this, other cognitive components, which we don't really have to deal with in the standard kind of room-to-room paradigm. And I know there's including the work that was discussed earlier, there's a lot of extensions to room-to-room, so I should really update this with other sort of newer data sets, but I think it gets the basic idea across. The other thing is the language complexity itself. So this is this question of basically, well, how many sort of tokens are we actually having to process? How much tracking are we having to do inside of the instruction? So importantly, note the touchdown also has this really high instruction length. And so in thinking both of these kinds of, in these data sets, what that means is that you're going to have a system which, when presented with these much larger paragraphs of text, has a substantially harder time actually figuring out alignment. And so this sort of notion of alignment and tracking is going to be common to both of these tasks, or both of these data sets. So that's the other reason for this. Even though the environments are reasonably simple, a single room, the instructions tend to have to be reasonably long. The next part is state changes and underspecified language. So this is, I think, where stuff starts to get interesting for me. So the first is, like I was mentioning a second ago, is the notion of heating and cooling and so forth. So let's try to take one of those things, and let's try to take the example of a high level instruction and see how this becomes underspecified. So if I have an instruction like place a hot bread slice on the counter, well, the first thing that has to happen is I have to find the loaf of bread, obviously. And the second thing I have to do is I have to slice it. This state change is immutable. I can't unslice it. And so that means that a lot of the search techniques that we were seeing, for example, even in the previous talk, I was just saying with dialogue, we're seeing a bunch of still navigation search happening. But a lot of the VLN models are very reliant, my own historically included, on basically being able to do backtracking. That you can't do that here, right? If you've made a mistake of this kind, you're out. And that's a little closer to reality. The same thing is also going to be true with things like cooking. So you put this thing in the microwave and you heat it up. Well, we aren't going to quite do the molecular modeling of heating up bread, but if you're aware, if you've microwaved bread, you kind of can't undo what's happened to it. So these are kind of the first sort of really interesting piece to me about this. The other thing is that we're going to introduce the notion of masks for object interaction. And as I noted a minute ago, I like to maybe repeat this just for clarity, for transparency, not robots, right? So discrete actions, no torques. But as a sort of baby step towards that vision, we want to be building models and interfaces that are actually eventually going to be able to transfer. So in this case, this is the example of wash the cup. And so if we have something like the following scene, we are the agent, we are holding this cup in front of us and we need to wash it. Well, we have a sink basin. So a discrete action would be something like put in. So we're going to have that. That's one of the simplifications that we allow. But we're now going to require that the agent know where it wants to put it. And the way we're going to do that is via this pixel level mask. So it now basically needs to understand the basin of the sink is where it needs to go. Once it produces both of those things, then the cup is placed inside. Now we have, again, a very high level task, in this case, toggle. But what does it have to toggle? It has to toggle that small piece of metal in the back, which is the faucet, at which point the water will turn on. And so again, the idea here is that we're taking a baby step towards actual robotics. And a baby step, very literally, very small. But it is the case that a lot of modern grasping techniques are going to assume that you can produce a mask before you actually go at it, like sort of a GraspNet style architecture. And so we kind of think of this as sort of one prerequisite technology in order to actually start to bridge that gap. So eventually, obviously, we should have actual manipulation. So then when you're presented with this, then there's this question of like, how should we go about modeling it? And so I want to present sort of philosophically how I think we should go about modeling it, and then sort of what is actually maybe done. So when we think about an underspecified language like this, for example, place a heated apple slice on the large table, as a human reading this sentence, there's a tremendous amount of existing knowledge that you just bring to the table that you can autocomplete here, right? So apple slice means that if it doesn't exist, I need to create it. What do I need to create it with? I need to create it with an apple. Heating, though it comes beforehand, is actually going to come afterwards because the prerequisite is that the slice exists. Then I have this large table. This is where it's going to finally reside. Creating the slice maybe has its own prerequisites. I need to collect a knife, locate the apple, and so forth. And then once I have access to the world, even if it's just spinning around in place, then I can start to fill in even more low-level details about how I would go about doing this. So maybe I notice that I see an apple on the table. I notice that I see a knife on the counter or by the sink. And so I'm going to try to execute those. So what we really want, I think, in the long run is some systems that can do this. We want systems that can take in this kind of high-level language and then can go about basically creating these kinds of generic or abstract plans, which are then instantiated slowly as evidence is accumulated. What we started with, and which has been improved on dramatically, is kind of a much simpler baseline, which I think everyone sort of wants to just see, which is how well does kind of a simple end-to-end tabula rasa kind of model work? In other words, if I take the entire paragraph of text, I encode it through something like, in this case, a BILSTM, I take my image, I throw it through ResNet, I take the features from both of those things, I concatenate them, stick them in an LSTM because I have some state that needs to be preserved. And then I go ahead and use that to produce via like a deconvolution, the mask and then a set of actions. How well sort of does that work? So I'm going to compare that and then a bunch of stuff that's happened since very quickly. So the first thing is what we found with our baseline and then a couple people afterwards is that performance was quite low. And we're going to measure performance in two ways, I guess sort of four ways, if you will. So there's success rate and goal conditions. So success rate here is the standard success rate that you're probably familiar with. So this is, did you complete the task? Sort of the full thing, got to the target, everything's where it's supposed to be and so forth. And we can do this for both seen and unseen environments. And then the second part is kind of a notion of sort of partial credit. So in particular, the idea with goal conditions is, well, maybe I was successful in the sense that I picked up the apple and I brought it to the counter or something like this, but I didn't get the second apple. Or maybe I picked up the apple and I sliced it, but then I didn't cool the slice or whatever else. I sort of want some notion of partial credit that's a little bit softer than success rate overall. So here's how poorly the sequence-to-sequence model does. A couple of models came immediately afterwards and really, really improved. Particularly, you're seeing substantial improvements on the seen tasks, though a little bit less so on the unseen. A number of things happened here. So the first thing was sort of improvements in terms of pipelining, improvements in terms of the pre-trained components, using object detectors rather than simple sort of single frame feature representations, things of this nature. Now, we still have quite a ways to go, though, because it turns out that this is not actually a very difficult task for humans. It's quite easy, in fact. And so when you put humans side by side with our models, it becomes reasonably obvious. So as I noted earlier, then there's this question of like, okay, well, how should we be going about this, and why is this hard? And so there's like a few couple hypotheses that you might throw in here. So you might say like, oh, the reason it's hard is because actually, you know, with cluttered scenes, there's so many different ways to describe them. There's a lot of lexical diversity there. These masks are maybe difficult to generate, particularly in unseen scenes. So every asset is built from scratch for every scene in Thor. And so maybe it's the case that like, oh, I've just never seen this type of faucet before, and so I'm having a lot of difficulty. Totally valid hypothesis. Another possibility is that we really just don't have good enough models of these kinds of scripts or program inductions, so they're not really sort of able to kind of decompose, particularly from the high level, all these different steps. Even when we give them the low level, they're maybe not doing good state tracking because there's sort of like too many things to keep track of. And so I want to just very quickly close on a couple of things that have happened in the last few months that I think are starting to make serious headway here. And the main sort of thing is explicit notions of maps and of searching. And so here's the table or the plot that I was just showing you a second ago with these models from earlier in the year. And so what we've seen is we're not actually hitting human, but I want to just sort of focus in on, you can replay that. But if you look at those unseen bars, so let me just do that again. So if we look at sort of where we were with these unseen environments, and then what has been happening in the last 6 months. So again, really far from human, but pretty substantial, really nice upward trends. And this, the first, big improvement here really comes from vaults. So he has this work that came out just a few months ago, where he's basically building these voxel representations of the entire scene, these 3D sort of semantic maps of the entire scene, and then is able to use that in order to perform sort of the navigation task, and sort of has sort of a notion of where to go at any given point and what options to interact with. So this, please read his paper. But this builds on, he's got this really nice body of work on quadcopters, and this really builds on that history of basically how do you build these kinds of representations, extracting depth maps and so forth. Simultaneously, we happen to have also had a very similar idea, though only in 2D. And so we have some new work as well on basically building out these kinds of maps and then using that for search. And so it means that if I know that what my next sub goal is that I need to perform, and I have at least a partial map of the environment, then I can produce some sort of distribution over where to search in order to execute the next step. The important thing about both of these works is that they actually have very impressive results using just the high level instruction. So I was saying one of the key goals here, right, is that we really want to move to a place where we're able to take sort of just this high level, very generic instruction and then actually execute it, sort of do that whole kind of understanding the prerequisites and understanding the planning that's involved. And so both of these models are able to do that and actually perform better than a lot of the models that are using low level instructions. And so that's very cool. So what this looks like in practice, since I don't have a good demo for vaults, I'm going to show you only ours, but again, please look at their stuff as well, is you have this agent, it's taking in these RGB images, it's trying to build a semantic map, again, in our case, 2D, and it has a set of sub-goals that it wants to try to execute. And so the way that it's doing this is that as it's going around, also that was very fast, I realize, so let me pause, oops, sorry, let me pause it. So if we get to this point, but the agent has seen some number of images, it's taking each of those RGB images and then producing an estimated depth map. It then takes that estimated depth and its predicted segmentations of objects, and then uses those to update this high level sort of bird's eye view map. And then using that map now, it can look at what it's supposed to be achieving, and it can start to actually move to the requisite location in order to perform each of those tasks. And so what you see on the right is the sort of set of sub goals by kind of being checked off. Our technique here is also based heavily on Devendra's Chaplot's previous work on doing this for VLN, but there's a number of things that have to be sort of generalized in order to work in this slightly harder domain. So one of the kind of key components here is this question of sort of where to look. And so here's a really simple scene. This is a very small scene, so it's reasonably easy. So we have, in this case, a bathroom, and the model has what you're seeing in different colors here is that the model basically has these kinds of regions where it believes that a toilet, a faucet, a bathtub, a shelf, and so forth are. And so in this case, if the agent is told to look for a faucet, then we want it to basically, regardless of where it's located at the moment, we want it to basically produce a some sort of map that says, here are the two places that you should try to look for a faucet. So a little more realistic, this is kind of this is actually the ground truth. Here's the estimated version. So you can see some similarities. So we still have kind of the toilet is being recognized. We've but it's more blurry now because these are all automatic. We've got the faucet. It's not sort of a nice perfect square. It's this kind of big mess. The bathtub is a big mess, but semantically they're basically in the right places. And so now, given this, what we do is we have the model produce a spatial attention over it, given the instruction. In this case, given the fact that it's searching for a faucet. And what you can see is that it basically puts most of its mass on the sink basin. And then we have a little bit of mass actually happening sort of at the end of the bathtub, which is also correct because there is a faucet here. but in general, maybe a little harder to get to, maybe a little bit less oftenly referenced in the actual data sets. And so the model has a sort of bias towards choosing this faucet. And so once we have this kind of map, then the agent can deterministically navigate towards that, see if it can then turn it on, perform the next task, and so forth. And so what I'm going to close with is I want to sort of talk about why this is nowhere near solved and what sort of has to happen moving forward. So here's this kind of base method, and I was telling you some of these metrics earlier. This is sort of goal condition and success rate. Here we have just on the validation data. And so we have both for the seen environments and the unseen environments. And we can include low-level language. We don't do anything particularly clever with it, and we get a small amount of improvement, but nothing to write home about. The really big changes come when we start adding ground truth segmentation, ground truth depth, or both. And so if you note the sort of success rate here, jumping from 20/24 to like 43/55. So this is kind of one of these things where we think about this as a language task, and it is a language task, but a really big part of this is just doing substantially better, vision. And then in our model, we also go ahead and test one more condition, which is that if we kind of come up with optimal sub goals, does that improve things further? And it does by another few points, by another 8 points or something like this, 7 points over here. And so there's definitely room there. But even with all of these, we're not at 100%. In fact, we're not even really all that close to humans. And the reason for that is because this model is not really carefully processing all of the low-level language, right? So another line here is basically understanding how to go in and open all the cabinets, look at the right one on the right, and so forth. And our sort of model doesn't have a way to reason about all of that. It's not doing state tracking necessarily as well as it should, and so forth. So vision is hard, but so is language. Sort of we have a lot of room in both of these places. So to close, oops, I messed up a transition here, but I started off by talking about this, and I said what goes in the gap here. And so this is not work that I'm part of, but I just think it sort of makes sense to plug. Is Jesse's new and Ashwarya's new teach data set. And so what they're trying to do is, I think, basically exactly what is in the question marks here of this little graphic, which is get us to somewhere where we're doing sort of navigation, we're doing interaction, we're doing dialogue, we're doing skill learning, task learning, all this kind of stuff all at the same time. And so they've just released this. I have not had a chance to play with it, but I think I figured I would plug it as kind of that, potentially that next step for us kind of as a community, as we start to think about interaction, both in terms of the actual world and in terms of with the human. And so with that, I will close. These are the first authors on the 3 papers that I was focused on. And so all credit goes to them, obviously. So with that, thank you for listening.
Okay, thanks, Professor Biggs, for his excellent sharing of RMM effort and film. Now is the question time. Is there anybody have questions for Professor Biggs? Yes, Yuan Kai.
I have a quick question for the last task. I saw the could you share the screen once again, Peter?
Oops, sorry. Share which slide again?
The last results on the last task. I saw that the results. Yeah, I saw that the results on the validation answer, the results are much better than on the validation scene split. So is there some explanation?
So you're saying like why is it that, for instance, it's sort of it kind of goes back and forth. So here, seen is better than unseen, seen is better than unseen, seen is better than unseen, but then starting with ground truth depth, Yeah, we're
Yeah.
starting to see that the unseen. Yeah, it's a good question. I don't have an answer to that, and why it sort of flips at the depth. It really does seem to be related to the depth issue. My hypothesis is that it's probably something kind of innocuous, so there's like the task. There's only a handful of rooms at this point in the validation, because the validation is quite a bit smaller than the test set, and so it really may just be that this is kind of, and I'd have to go check this, so don't don't take this to the bank unless but my guess might be that that there are a couple of larger rooms in the unseen environment, and so therefore ground truth depth is going to have a substantially bigger, but because it was sort of a random split at that point. But it's a very good point. I have not investigated, so yeah, it's worth checking.
Yeah, maybe some data bias maybe there, right?
Yeah, for sure. Because basically, that's why I was showing this really silly example of the bathroom is kind of a very small room. You can basically, the agent spins around and it gets almost basically all the depth it needs effectively immediately. But for the living room, for the kitchen, it really does have to explore for a bit. And there is another method, by the way, on the, oops. So this AM SLAM, so I don't know that much about it, but I'm told, so it does quite well. It does a little bit better than us actually on the scene conditions. And I believe that they actually do pre-explore of the environment. Build their entire depth map in advance, sort of like a proper SLAM technique, and then start executing the task, where we're sort of doing it online. And so they may not have that kind of a gap, right? It may be that they end up with something more consistent because they sort of do that exploration process.
Yeah. Okay, thanks for your answer, and thanks for the wonderful speak. Thank you.
For sure.
Okay, I have a question. I appreciate RMM. It's a very impressive work, but I'm still curious how the RMM agent is able to generate good natural language sentences. Does it utilize prior language knowledge from BERT also?
Yeah, right. So I actually, so thank you. I think it doesn't produce very good natural language sentences. But
okay. I think it's good. I think it's good.
And I think that your recommendation, or what you're hinting at, is actually correct, which is like the thing that we've not had a chance to do, because I just haven't had someone who wants to work on it, is sort of update that model with a substantially better generator. I do have a number of thoughts on what that looks like. I want to maybe add sort of one potential strength and one potential caveat. So the benefit of using something in domain like that, so using a simple kind of seek-to-seek style model, is that it is entirely in domain. I don't have to worry about basically as much lexical diversity and things like this, because it just would never have seen those types of things. It's basically only knows language about rooms.
Yes.
The flip side is that it doesn't have nearly as much training data as if I was to pull GPT or some other kind of thing, or some captioning model like Oscar or something like this off the shelf. And so I think that the question that I don't have an answer to is there a way to kind of leverage both? And in particular, I want the fluency and the robustness of those larger pre-trained models, but I also want the sort of domain specificity of the smaller model. And so something, for example, that you could imagine doing is actually trying to just freeze most of those models, and then sort of only have like a few layers that are fine-tuned on this kind of smaller data. I don't think you want to use like an RL training paradigm with those big models. I think it's just the signal is going to be very sparse, and so I worry that wouldn't work that well. And then an extension of this that I think is also very difficult is that most of these models, so at least in the case, I think Oscar is trained on some questions, but things like GPT and stuff like this are not particularly good at QA, because they're sort of not trained. They're trained to sort of generate sort of nice paragraphs. They're not really trained on question answer to generate answers, and so there may be some amount of additional work that needs to be done before it would be put into this environment, right? So you could imagine that the first thing you do is try to train it to learn the style of question answer pairs or something like this a little bit more generically before you then try to then fine tune it in this environment. So anyway, it's not a complete answer to your question, but I think it's basically your intuition is correct, but I think there's like a couple of little places that one might stub their toe if you try to sort of do it naively. And I'd be interested to see yourself or someone else actually try to address those things and come up with some kind of clever ways to transfer that kind of knowledge in. We also, for example, are still using in that network, we're still using single, I'm 99% sure we're still using just a single visual feature for the entire frame. And you could imagine that, given that these models are so good at doing object detection, that you could maybe leverage that and then have be like, oh, I see a blank. Is that the direction that I should be going? Things like this, which we're not getting those kind of phenomena right now. So I think that would be very cool.
Okay, yeah. In RMM, there is two agents that question and answer together, right? So I have long before I have a question that how does these two agents have make some pass code or something? For example, when an agent asks, should I go left? And agent answers, yes, you should go left. Actually, the agent means go right, flips the left and the right. Yeah, they have a
so
passcode.
this definitely happens, but it also happens with humans.
Oh yes.
So if you put two humans in a they will also make the same mistake. So I don't actually have an answer to how to address that. It may be the kind of, a naive answer would be to try to include some amount of template training or something like this to try to kind of break it of that kind of habit. But yeah, this is definitely a thing that happens. We don't have quite as much of it in the sense that the CVDN dialogue stuff is collected with a bird's eye view, a first person view, not a bird's eye view. And so you are seeing exactly what the person should do. I think this is one of these things where I mentioned the teach data set. I think that might be slightly harder because if you have, I believe they have a bird's eye view in that one. And so you have to do perspective shift to sort of, and so it's quite possible that humans also make more mistakes. And so therefore you'll see more errors even in the training data in that case.
Okay. Thank you, Professor.
Yeah, of course. Thank you.
So we should move on. So let's welcome the next speaker, the Dr. Professor Peter Anderson, a research scientist from Google Research, to share his recent works.
Hi, Feng there. I hope, so I think you have the recording of the talk, but I'll be around for Q&A afterwards.
Okay, yeah, I have the recording.
Perfect. Hi, folks. My name is Peter Anderson. I'm a research scientist at Google, and this talk is about massive data sets for language-guided navigation agents and where to find them. Recently, we've seen a redefinition of what's possible for state-of-the-art vision and language models. And I'm talking in particular about models such as DALL-E and CLIP from OpenAI and the Align model from Google. And what's particularly amazing about these models is that they're proficient at multiple tasks. They have zero-shot capabilities. So, for example, a model such as CLIP can achieve very good results for classifying images from ImageNet without using any of the ImageNet training data. And these models are also surprisingly compositional in the way they are able to combine fine-grained concepts. So if we look, for example, at an image retrieval task using text and image embeddings from the Align model, we can see that the model clearly distinguishes between very fine-grained concepts such as a Van Gogh Starry Night details versus a Van Gogh Starry Night in black and white, or on a canvas, or in a dark wood frame. which is very impressive. If we look further at compositionality, here we're doing an image retrieval task using a combination of an image embedding with a text embedding added or subtracted. If we look at the example in the second row, the image embedding of a butterfly on a purple flower. If we subtract the text embedding for flower, we can retrieve an image of just a butterfly, or we can change the color of the retrieved image by subtracting the text embedding for orange. And we can even add the text embedding for rose and retrieve an image of a butterfly sitting on a rose. So this is really quite remarkable. And the reason for these advances is not so much new modeling techniques as simply using much, much larger models and much, much more training data. How much training data? So for the Align model, it's trained on noisy web images, image and text data. So you can see from these examples here, the text data is actually, really quite noisy, but the training data consists of 1.8 billion image text pairs for the English only version of this model. And so the power of these models really comes from the huge amounts of data that are used to train them. And so you might well ask, why am I talking about this in an embodied AI workshop? And the reason is, well, first of all, my particular interest is in language-guided embodied agents. And so one problem that we work on quite a bit is language-guided navigation agents, or vision and language navigation, which is this sort of task that you see demonstrated here. We want to provide a natural language instruction, such as exit the bathroom, turn left, and exit the room using the door on the left, wait there. And what we want is to be able to train an agent that can follow these grounded natural language navigation instructions in a photorealistic and previously unseen environment. And the observation that I want to make is that the training data for tasks such as this is really very limited. And if we just had billions of instruction trajectory training examples, I think it's very, very likely this task would be much easier. And although this observation is quite flippant, on the other hand, it's actually quite serious because many of the limitations of the current models, such as overfitting to the training environments and poor generalization to unseen environments, a lot of these problems would likely just evaporate with more training data. And so the question is, well, should we not, consider, is there a way that we can stop mucking around with data sets with thousands and tens of thousands of examples and look for hundreds of thousands or even millions of training examples, and how would we possibly do this? And this is the research program I'd like to talk about today, guided by this question. How can we use the available resources we have to generate massive data sets for training language-guided navigation agents? So my argument is that there's 4 parts to this research program. First of all, we need to generate more environments. And one possible way of achieving this is by converting static images and videos of places, which are available at huge scale, into interactive training environments that would allow an agent to somehow move within the image or the video in order to learn navigation. Secondly, if we create these hundreds of thousands of new environments, we would need to annotate them with training tasks, which means generating high quality navigation instructions from a model. Thirdly, using model generated instructions, we naturally need to figure out a way to evaluate those instructions for quality, to ensure the quality of the training data. And finally, even though we want to generate these environments and generate these instructions, we obviously still need to collect quite a lot of high quality human annotated navigation instructions to sort of bootstrap this system, to train the instruction generator and to evaluate the navigation agents that we train. And so this is a research program to look at ways that we can scale the training data for language-guided navigation agents far, far in advance of what's available currently. And today I'm going to talk in particular about these three aspects of the problem, beginning with the problem of generating environments. So first of all, what's the kind of current situation? So typically for training embodied language agents, there are different simulators and different data sets, but they're typically based on underlying environments from data sets such as Matterport 3D. And there are some others such as Gibson as well, but generally they have they're at a similar scale. And Matterport 3D contains 90 environments, each reconstructed with a Matterport camera. And as a consequence, I guess, of the relatively small number of environments, what we see when training vision and language navigation agents is that there's a lot of overfitting, that performance of these agents might be quite good in the training environments, but it drops significantly in unseen environments. And so the concept I would like to investigate right now is whether we could take images and videos of places that are readily available at massive scale. Even looking at internet videos, there are hundreds of thousands of real estate walkthrough videos on the internet. And my question is, can we take these static images and fixed videos and somehow make them interactive and convert them into interactive training environments where an agent could learn to navigate? And so what does this look like in practice? Let's walk through it using this example on the right-hand side. Suppose I had, as an example, just a single image as an input, which is image 1 at the top left. And now I'm training an agent that wants to move in such a way as to follow the yellow arrow, which is moving to position 2, shown in the floor plan view at the top right, which is only indicative and not used by the model. What we'd like to do is generate the image in the second row, the prediction of what the view would look like from that new position. And so on, if the agent moves again, following the yellow arrow to position 3, what we would like to do is generate a prediction of what it would look like from that position. And then what we've effectively done is made this image interactive. And so we have actually proposed a model that can do this. The predictions in position 2 and 3 are the outputs of that model. And you can see how they compare to the actual ground truth on the right-hand side. One fairly interesting aspect here is that in the ground truth, in this real environment, the ceiling of this kitchen is actually painted with a fresco of clouds. Now, a model has never seen that. This is an unseen environment, and so the model does not predict that. But nevertheless, it comes up with a fairly plausible prediction of what it would look like to follow those arrows and to move and see inside the kitchen area. So that's the proposal that we're making, to take static images and potentially videos and convert them into interactive environments. And so what we're really proposing is actually a world model for indoor navigation. So typically world models or model-based RL has previously been explored in the context of game environments such as Doom and Atari games. Here, as I'll show with a video, here we're taking this same concept and applying it to indoor environments. So here's a video showing some of the outputs of our model, which we call PathDreamer. Each of these outputs is generated from observations at a single point, and then by allowing or providing some trajectory to the PathDreamer model, and the PathDreamer model then generates observations along that trajectory. So here's a new example. This is the starting image, and these are the predictions from the model as we move in different directions around this building, including around the corner. So we tackle this sort of room reveal problem of what things might look like if we go around the corner. And certainly you can see the model does a fairly nice job of generating consistent and plausible outputs of what this might look like from different parts of this building. one thing you can see, and we're sort of deliberately showing, how far you push this model before it starts to break down. And in general, it takes around 4 or 5 meters before the model starts to break down in its predictions. So one comment I want to make as well is that we've motivated this world model, this path dreamer model, using the idea of data augmentation, turning static images into interactive environments and using them for training. But world models can be used for many other purposes as well, not least of all is sampling-based planning. So, for example, an agent equipped with a world model can reason about the consequences of its future actions before it takes them and use this to come up with better plans. So let's dive in and have a little look at the details of this model. It's based on 2 stages. The first stage is a structure generator that deals with the segmentation and depth components. And so the model actually takes in segmentation images and depth images as an input. Now, these could be predictions from another model, but in this case, in what I'll show you today, we're using ground truth, depth, and segmentation inputs. And we then represent these depth and segmentation images as a 3D point cloud, which is reprojected into a guidance image based on the motion of the trajectory. From there, an encoder-decoder stack is used to infill the guidance images, and we also condition on random noise vectors in order to try to capture some of the variability in areas of the image that are completely unseen, for example, when the model looks around corners. The second stage of the model is the image generator. Again, we use a point cloud representation reprojected to a guidance image and a stack of multi-spade blocks in order to generate the hopefully photorealistic RGB predictions of the model. So let's have a look at another example of how this works. If we're given these 3 images from a single observation point as input, so we have the depth image, the segmentation image, and the RGB image. And by the way, all of this data is 360-degree images in equirectangular format. We can then do a rollout of predictions along some planned trajectory, 1 step, 2 steps, 3 steps, and so on. And you can compare the RGB predictions of the model in row 3 to the ground truth of the actual environment, which is previously unseen in the bottom row. And in general, the predictions from the path dreamer model are quite plausible. One area where I can highlight a mistake is in terms of the ceiling rafters, where the model does not actually realize that a rafter must go all the way across the ceiling in order to actually carry any load. So that was an example of a rollout. I want to show some examples as well of the kind of plausible alternatives that the model can produce by sampling different noise vectors. So on the left-hand side here, we see the guidance images that are the reprojected point clouds used as input to the model. What's important here is the black regions. These are areas where the path dreamer world model has not seen any part of this environment. It has no information about what could be there. And so these are the areas where sampling different noise vectors will produce different results. And so you can see the path dreamer predictions on the far right-hand side. For a particular noise vector, it's predicting a window, a chair, and a table. If we sample a different noise vector, it can predict a bed with a cushion and a chair, or a different type of table without a window. So you can see there on the right-hand side, these kind of different plausible outcomes that can be produced. Finally, I want to just briefly introduce a small experiment we've done for using the path dreamer world model as part of a sampling-based planning approach in the context of vision and language navigation. So what we do here is we roll out using the VLN agent to kind of plan ahead out between 1, 2, or 3 steps into the future by either interacting with the path dreamer model or the ground truth, which is the actual environment, effectively looking ahead, or a baseline, which represents using the information from the navigation graph, but without any visual properties. And so what we can see in these results here is that the green baseline improves performance with forward planning over 2 or 3 steps, because it can use some information about the structure of the navigation graph, about the structure of the navigation possibilities that are there. The path-streamer model does significantly better, though, by providing plausible visual observations that might be seen in the future. And the path-streamer model closes about half the gap to the ground truth in this example. Right, so I've talked about how we might use the path-streamer model to generate environments from images and videos. I won't be talking about generating instructions today, but I do want to discuss our work on evaluating instructions. So to put this in context, when we talk about an instruction following agent, we're talking about a mapping, a model that maps from instructions through to some trajectory in a photorealistic environment. An instruction generator performs the inverse operation. It takes some trajectory represented with visual and possibly geometric representations and converts that to a grounded instruction that hopefully a person could follow. Now, while evaluating an instruction following agent is at least conceptually quite straightforward, we just compare the agent's path to the reference path. Evaluating an instruction generator is more difficult. In theory, we can compare the generated instruction to some reference instruction, but what's not clear at all is what metric we should use for that. And so in this work, this is the question we investigate, is how to evaluate model-generated navigation instructions. So our first step is to assemble a large pool of navigation instructions of varying quality and styles. So we begin with human instructions, and we also perturb those human instructions in various ways by swapping directions, such as left and right, by swapping entities, such as in this example, replacing kitchen area with door and door with kitchen area. And we also swap phrases by reordering them in the instructions. This creates a variation in the quality of the navigation instructions. To this group, we add navigation instructions generated from 2 existing models, the speaker follower model and the environmental dropout model. And finally, for even more variation, we add template-based instructions, which we call crafty, to this pool. And here you can see an example of a crafty instruction. These are based on the ground truth object annotations in the Matterport dataset. And so these should be factually correct, but they're quite long, which can make them difficult for people to follow. So the next step, given this large pool of different navigation instructions, each describing the same paths in the Matterport environments and based on the paths from the room-to-room dataset, we now perform human evaluations. To do so, we use Pangea, which is a panoramic graph environment annotation toolkit that we recently open sourced, and we collect 3 human evals per instruction. So for example, here you can see the interface that the human wayfinders are using as they attempt to follow these instructions. They're able to kind of look and move around in these environments, attempting to follow the instruction at the bottom of the screen, which in this case is leave the room and turn left. With the wooden door behind you, keep walking straight, stop after you go down a few stairs. You can just see the few stairs in view now. So using this, we will basically evaluate the quality of the instruction based on how well our human wayfinders were able to follow it. And we measure that using navigation error, the difference between the goal reached by the navigator and the actual goal location, and also success rate, what percentage of times that navigation error is less than 3 meters, and so on. And so here are the results. And what's interesting is first of all to look at the performance of the existing instruction generators from previous work, the speaker follower model and the environmental dropout model. And it's interesting because the quality of the instructions that these models are generating is actually only slightly better than Crafty, the template-based approach, although it must be said that Crafty has the benefit of using the ground truth object annotations. The existing instruction generators are much worse than even the adversarially perturbed human instructions, and far worse than the gold standard human instructions. And the reason this is quite interesting is that these existing instruction generators have already been used very, very successfully for data augmentation, typically improving the performance of instruction following agents by around 5%. And so that's somewhat surprising, given that it turns out that compared to human, the quality of these instructions is quite poor. And so that does suggest there's substantial headroom here to improve not only the instruction generators, but also the quality of the VLN instruction following agents when these generators are used for data augmentation. Now, the primary question of interest here is what evaluation metric we should use for generated instructions, for navigation instructions. And so now that we've established a large pool of navigation instructions of varying quality, and we have human evaluations, our aim is to identify which evaluation metric out of the automated metrics will closely correlate to human performance. And so these are the automated metrics that we look at. We consider textual comparison metrics such as Blue, Cider, Meteor, Rouge, and Spice. All of these metrics require some reference instructions for comparison. We also consider a model-based approach based on BERT score. Thirdly, we consider using vision and language navigation agents as instruction followers and consider evaluations that are based on the instruction following success of these computational agents. The advantage of this approach is that no reference instructions are needed, only the reference path. And finally, we consider a compatibility model, which we propose in this work. And the compatibility model is effectively a dual encoder. It encodes in the one stack a visual and geometric representation of the trajectory, and in the other stack the textual instruction. And it's trained with contrastive loss and large batch sizes to learn to associate which trajectories and which instructions are matched. And so this can then give us a score, which we consider as an alternative evaluation metric. So let's look at which of these metrics correlate with human wayfinding performance. And there's two ways of looking at this. Firstly, we consider a system level evaluation. So this is for when we're wanting to evaluate an instruction generating model. And so we aggregate the scores for each model. And as it turns out, the only one of these scores that has the desired correlation with human evaluations is the SPICE metric, which is negatively correlated with navigation error and positively correlated with success rate and other quality measures such as SPL. And quality here refers to the quality of the instructions as assessed by the annotators on a 5-point scale. So this is a surprising finding because it turns out that Blue score, which is typically considered for many text generation tasks, turns out to have no value here whatsoever. And so for evaluating instruction generation models, i.e. system level evaluation, the SPICE metric should be used. Now, the other question is, what about at the instruction level? What if we want to evaluate the quality of an individual instruction as opposed to a model? And in this case, we don't have the ability to aggregate our scores over many, many different instructions. And so the variance of the evaluation metric is much more important. And so it turns out that in this case, the best approach is to use a compatibility model, like the dual encoder that we proposed earlier. And almost as good as this would be to actually use a language-guided follower agent. And it turns out that actually at the individual instruction level, SPICE is not effective, and neither are any of the other textual evaluation metrics. And there's also an additional advantage of using computational models and navigation agents for scoring these instructions, and that's the advantage that they don't require reference captions. So overall, I think there's a bit of a warning here for the creation of new tasks. Very often we see new multimodal language generation tasks are being proposed, and automatically BLUE score is considered as the evaluation metric. And the results here, which show that in this particular case, BLUE score has no value whatsoever, suggest that we probably should be deeply suspicious of any new tasks that are evaluated with BLUE score, unless a human evaluation has been done that shows that BLUE score actually correlates with the scores from human evaluation. So having talked about our work on evaluating grounded navigation instructions with some firm conclusions, I now want to talk about the final aspect of this program, which is dataset collection. So recently we collected a new dataset, which we call Room Across Room, or RXR. And this is effectively what the data collection interface looks like. On the left-hand side is the view that the annotator has. They're able to move around and control where they move as they're following a navigation path that's marked with arrows and spheres in the environment, which you'll see. As the annotator moves around, they record with their voice a description of the path that should be taken. I'll show you at the bottom the transcribed text as that description is described. And on the right-hand side, you can see out of the full 360-degree view, which parts of the environment the annotator actually looks at, which we also capture. So let me play this annotation example now.
Now you're standing in front of a closed door. Turn to your left. You can see two wooden steps. Climb the steps and walk forward by crossing a wall paint which is to your right side. You can see an open door to your left side. Enter into it. This is a gym room. Move forward and walk till the end of the room. You can see a grey colored ball to the corner of the room. Stand there. That's your endpoint.
So that's the interface that we use to collect a large-scale data set. And so you might wonder, well, why do we need a new data set for vision and language navigation? So there's a couple of reasons, a couple of things that motivated this work. Firstly, the majority of work in this language-guided navigation or vision and language navigation space is English-centric. So we wanted to create a data set that was multilingual. In this case, it includes English, Hindi, and Telugu. Secondly, hopefully this has been well motivated by now, but we wanted to increase the scale. And so the RXR data set is around 10 times the size of similar data sets. It includes over 100,000 instructions and something in the order of 10 million words. It also contains fewer path biases in terms of the way the paths are constructed, and the viewpoint coverage is more uniform compared to previous data sets such as room to room. Fourthly, we include a follower demonstration of every single path, which is a nice way of ensuring the quality of the data, but it also provides additional signal in terms of a human blow-by-blow description of exactly how a person follows that path. And finally, hopefully this was clear from showing you the annotation interface, but we capture this spatio-temporal grounding. So by recording voice and transcribing it to text, rather than using text input, which was used by the previous data sets, we're able to align every word in the instruction with what the annotator was looking at as they recorded that instruction. In order for that to work, there's a neat idea that we borrowed from previous work on the localized narratives data set. And so basically, in order to get the alignment between each word in the instruction and the pose trace, which captures what the annotators were looking at, we first perform an automatic transcription of the voice recording, and then we compare that with the manual transcription created by the annotator. And by aligning the two, we're able to propagate the timestamps from the automatic transcription into the manual transcription. So ultimately, the output of this setup is a manual transcription that's timestamped to match the pose trace, indicating what the annotators were looking at. And by the way, our complete annotation toolkit called Pangea has been open sourced, which performs all of this work. So to put that in perspective, here's another view of that same annotation, which shows the path taken by the annotator in the context of a 3D mesh of the environment, and the color coding between the arrows and the light cast by the annotator's camera view aligns to the words in the text instruction shown on the right-hand side. So this is exactly what the spatio-temporal grounding that we've collected can look like. We can also look at this in terms of image space rather than a 3D mesh. So it's very interesting to see when we follow the movements made by this annotator and look at which pixels at each point in time of the 360-degree image, which pixels they actually looked at. You can see a nice alignment here between, say in the second image, the wall painting, which is seen in the image and then mentioned in the instruction, and so on. And so this is a really nice alignment between image and text, which we hope will be useful for training in various ways. And you can see a very similar alignment. So this is for the follower task, where a separate annotator is charged with following this navigation instruction. And again, we see a very similar alignment between the vision and the text. Just to briefly survey some of the interesting linguistic phenomena in the RxR instructions, in this case, in comparison with the R2R dataset, because the instructions and paths are generally longer, we see quite a lot of co-referencing. There's also a lot of sequencing in terms of an ordering that's provided to the instructions. We see a lot of mentions of allocentric relations, such as a window with a black folding table under that. So the position of the table is described with respect to the window as opposed to the observer. And there's this interesting and fairly new phenomenon for these data sets, which is we call state verification, where the annotators will frequently describe nothing more than what you should see at this point, and that can be used to verify that the instruction's been followed correctly so far. So based on this data set, we've released a number of interesting challenges. The RxR challenge is a multilingual vision and language navigation challenge using the RxR data in Matterport 3D environments. And in this challenge, the agents navigate through a graph-based environment, which is the kind of typical approach for these styles of data sets. We've seen some interesting advances on the leaderboard, and this is open for ongoing submissions to try to close the gap to human performance. Now, as well as the RxR challenge, we've recently also released the RxR Habitat Challenge. And so this uses the same RxR data and the same environments, but in this case, it combines with the Habitat Simulator, which allows for a low-level continuous motion in the environments rather than using graph-based environments. As you can see from this example here, this is a very, very difficult challenge because it involves not only multilingual language understanding and grounding, but also low-level control of the agent. To help get things started, we do provide starter code in PyTorch, and there's a leaderboard as well, which is available on an ongoing basis. So thank you very much. I hope the talk's been enjoyable, and certainly hope that other people have found this research program exciting. And I would like to finally acknowledge many of my awesome collaborators who've worked on the 3 projects that I've outlined so far. Thanks very much.
Okay, thank you, Dr. Anderson. Now is the question time. Is anybody have questions for Dr. Anderson? I have a question. For PathStreamer. I think the module with the structural prediction is amazing. It generates a precise room structure for the next step and greatly improves the decoding performance. So that's my understanding, right? I think the structural prediction is critical. Yeah. So, however, the structure largely rely on the point cloud map converted from previous scene depth sequence, right? Does the PathStreamer's performance still good at the beginning of the navigation trajectory? For example, the first step, second step also, without a accurate clouding map. Yeah.
Yeah, great question. So most of the evaluation we did is just using a single input observation. So there's not a large history of context that it's using, but it is using the ground truth depth image and segmentation, which, as you point out, you know, what happens when you sort of relax that assumption. So what we can do is switch it so that the depth input is the prediction from a model, and the segmentation input is the prediction from a model. We're actually been doing that in some follow-ups to this work, and we've actually sort of reduced that reliance so that it doesn't need ground truth inputs anymore. And yeah, with the correct training, that could still work just as well or better. So we're sort of continuing to develop on this thing to improve it further.
Yeah.
I have a quick question for Peter. So do you have any thoughts on what happens if you work with videos that have other humans in them? Like, I'm just thinking about this sort of like, oh, you have all this HGTV or whatever, but like a lot of those, there's like, you know, there's people walking around. Does that sort of like completely break the paradigm moving forward?
Yeah, it does at the moment. This is a question we've thought about a little bit, but haven't done anything about yet, is what about dynamic environments and modeling those? So that's completely not handled in the PathStreamer setup at the moment. Having said that, like there's this whole genre of kind of real estate walkthrough videos where there actually aren't any people in them. They're basically a static scene. And so that's sort of suitable, we think, for, you know, training this type of model, and also using it as input and inference time to sort of make those environments interactive. But yeah, we've definitely not modeled like anything dynamic, and I think there's interesting questions about how to introduce that. Particularly if you want to use this as a, you know, more of like using it as a world model for kind of planning, you know, for a robot, then you can't just survive in environments without people. That's not going to be very useful if you do. So.
Yeah, I was even just thinking about from a subtraction standpoint, like how much more data do you get access to if you can basically like edit out humans from those videos, not necessarily even when they're interacting with them, but just sort of presumably there's a lot of first person view video of scenes, but there's dynamic agents in them that maybe if you can sort of do this thing where it's like, well, they pass in front of something and then you can, but then they move, and so you can sort of do some infilling from another scene, and so you can sort of reconcile what that would have looked like if it was an empty. I realize it's kind of a larger question, but I was just thinking about how much more data there might be if you can handle, yeah.
I think, so one thing that's interesting in this space, you guys may have seen before the mannequin challenge, that was popular a few years ago when people took these videos where everyone sort of froze and stayed completely still as the camera moved. And so there was some folks in Google released this semantic and challenge data set where that data was ideal for training depth prediction models. And I think from that data, we could probably produce a pretty good model that would allow you to identify people and then kind of, mask them out. So it might be possible to leverage something like that to kind of do what you're suggesting. And if, if you mask these things out of the point cloud, then the model will just kind of generate something in that gap. So.
Cool, it's right, Grant.
Okay, due to the time limit, we have to move on. Now we are glad to invite Professor Dov Bratra from Georgia Institute of Technology to share his recent works. Sorry, due to some technical limitation, we have to invite the next speaker, Wenguan Wang, a postdoc from ETH, to share his work.
Hello, everyone. I'm Wenguan Wang. I'm so glad to be here to give this talk. In this talk, I would like to introduce our recent work on embodied navigation, mainly around the three themes: active perception, long-term planning, and multi-agent collaboration. The basic idea of embodied AI was proposed many years ago. When we try to introduce an AI agent into real world, things are very different. This is because many of existing AI agents are developed in factory environments. However, in real world, the embodied agents is to actively interact with the environment. The agents should be highly adaptive to the changes of the real world, and they should be also human-like. For example, they should be able to use different social communication skills and will understand our communication signals. Not only verbal communication, but also non-verbal communication, such as some body language, gesture, social gaze, and so on. So the embodied agents can achieve nature and smooth human-robot interaction. So we can observe a recent shift from internet perception to embodied AI. Traditionally, in computer vision, we developed different algorithms to interpret the data collected by our human beings. These data are typically downloaded from the internet. However, for the embodied agent, they need to move around for information gathering and decision making. They even need to learn from the data captured by themselves. So, in recent years, many different simulators, 3D environments, datasets, and different task settings are proposed for embodied perception. Along with this exciting direction, we put our focus on embodied navigation, which is a very fundamental basis for building intelligent robot agents. Our recent work addresses three crucial elements for developing more intelligent embodied navigation agents, namely active perception, long-term planning, and multi-agent collaboration. First, for active perception, a navigation agent is desired to actively collect visual information from surrounding environments for better decision making. With this insight, in our ECCV work, we studied the problem of vision language navigation. In this task, the agent needs to navigate a realistic 3D environment to reach a target location by following human instruction. Existing real language navigation agents are typically built on sequence-to-sequence model. They take the navigation instruction, current visual observation, and the previous navigation actions as input, and generate a current hidden state of the navigation, and finally predict the probability distribution of all the available navigation action candidates. However, with such a simple sequence-to-sequence model design, existing navigation agents cannot handle the uncertainty caused by ambitious instructions and partial observability. Here we show a tiny example. In this case, the agent is located at the bathroom and is instructed to leave the bathroom and walk forward along the pool and finally reach the target location. However, this is very difficult for the navigation agent to complete this task. From this picture, we can find that there are 2 doors in the bathroom. So which door is the correct direction? It's very hard to say. The agent, like our humans, has a limited receptive field. So here is the whole thing that the agent can observe. So it is hard to make a confident navigation decision at this moment. So how our humans handle this situation? Actually, our humans perform navigation very robust. In this case, we will first randomly choose a door for exploration. We move forward a few steps, and then we find this direction is wrong. Then we go back, and we choose another door for further exploration, and we find the pool, and we know this direction is correct, and finally we reach the target location. So this case shows the importance of the active perception, and this also motivates us to propose an intelligent agent. This agent is equipped with an active exploration module, thus to achieve such an active perception ability like our human beings. Basically, in addition to traditionally used navigation module, we actually use an active exploration module, which aims to learn when the exploration is necessary, which part of the surrounding is worth exploring, and which kind of information should be gathered from the environment to support more robust navigation. So, to achieve this goal, we design a specific reward for reinforcement learning. The first term refers to the distance to the target location after the agent makes exploration, while the second term refers to the distance to the target location before the agent makes exploration. So that means after making exploration, if the agent makes a good decision, this decision will make the agent more close to the target position compared with the situation without using the exploration. So with this useful exploration, the agent will receive a positive rewards. Instead, when the agent receives a negative reward, that means after exploration, the agent makes a worse decision. With this decision, the agent is even far from the target location before makes the exploration. Then this negative reward will cause the agent to change its navigation policy, exploration policy. To facilitate training, we further propose a curriculum learning strategy. Basically, at the beginning of training, our agent is only allowed to explore the nearest neighbors at each position. So the exploration policy is very easy to learn. After the training loss converged, we allow the agent to make some multi-step exploration. And then the agent will learn some more hard policies for further exploration. In practice, we find such kind of strategy is very useful. They can boost our performance and training speed. With such an active perception ability, our agent gains very impressive performance on the famous room-to-room dataset navigation sightings. This table shows our ablative studies. The first line is the basic agent without using any exploration. And for the second one, we can find that if we just let the agent make one-step exploration before each step navigation, we can gain better performance. This shows the advantage of active perception. And in other baselines, we let the agent automatically learn when and where to make multi-step exploration. The performance is further improved. Here we give a real example. At the beginning, the agent is towards this direction. However, the navigation instruction is wrong. It instructs the agent to go straight, but the agent faces another orientation. In this challenge case, our agent first explores this direction. Although this direction is wrong, after a few navigation steps, the agent collects more information along this direction and goes back. With the collected information, the agent can make a more reasonable navigation decision, and he chooses the correct direction for navigation, and finally successfully reach the target location. This is a more detailed example. The basic agent is confused by the ambitious instruction. Travel to the end of the hallway. This causes failed navigation. In contrast, our agent first explores the wrong direction, but it finds the observation is inconsistent with the instruction. So, with the collected information, it makes the correct navigation decision towards the opposite direction. And our agent finds the critical landmark false. Then our agent reaches the target location successfully. The second part in this talk is about long-term planning. This is also very crucial for visual language navigation. The basic idea is to let the agent directly and immediately access their past experience or observations over long time scales to achieve efficient planning. Here we give an example. Here is the language instruction, and we show the ground truth navigation path in red color. In this step, agent makes a wrong decision, and it needs to go back and turn to a correct direction. For existing sequence-to-sequence model-based visual language navigation method, it is hard to achieve this goal. This is because the sequence-to-sequence model just store all their past observations as the neural network hidden states. Thus, they cannot directly access the information at a past moment. And the network hidden states cannot capture the environment layouts. Thus, it is hard to make long-term plan. So we build a structured outside memory. It can accurately memorize the perceptions during navigation and serves as a structured scene representation to capture the environment layout. This allows the navigation agent easily access the global action space, since all the previously visited positions are stored in the scene map. Our scene map is structured as a directed graph. This can maintain the topology structure of the environment. In this graph, the nodes refers to visual representation of some essential landmarks, and the edge stores the geometrical information. Thus, we can achieve fine-grained instruction grounding. Some visual landmark-related instructions, like table, television, can be associated with the node features, while some motion-related instructions, like go forward, turn left, can be associated with edge information. With the global and structured action space, message passing-based reasoning can be conducted. Moreover, after several navigation steps, the navigation space will become larger and larger, since more and more regions have been visited. In practice, we find such a large action space will make our policy learning very hard and make the converge very slow. So to address this issue, we propose an exploration-based decision-making strategy. The frontier-based navigation has been widely explored in robotics. Here, the frontiers indicate the point at the boundary of no regions of a map. So with the concept of frontier, we make a two-step decision-making strategy. In the first step, the agent selects a frontier as the subject goal to navigate. Note the number of frontiers is much smaller than the build map. Then, after reaching a certain frontier, the agent will further choose a certain direction around the frontier for navigation. As the number of the frontiers and the sub-region around a certain frontier is much smaller than the whole navigation space. This will make our agent to easily learn the navigation policy. Moreover, for the frontier selection, the policy is learned in a navigation utility-driven manner. Doing reinforcement learning based on online policy learning, the agent is rewarded at each frontier selection step if the agent gets closer to the navigation destination. So this is different to previous robotic control methods, just selecting frontier based on some heuristics, such as maximizing the information gain or minimizing the moving cost. Here we give a visual example. The blue agent chooses a wrong direction at the beginning, and finally it fails because it's hard to return the correct direction. In contrast, our agent, the right one, it can easily change its navigation direction by using the scene map. And finally, it reached the targeted location successfully. Here are some quantitative results showing the effectiveness of our idea. The last part of this talk is about multi-agent collaboration. This is also a very interesting direction, since it is crucial to let the agents achieve human-level collaboration and accomplish the mission efficiently. It is believed that the next grand challenge of artificial intelligence is to answer how multiple intelligent agents could learn human-level collaborations. Moreover, the field of multi-agent reinforcement learning is repeatedly expanding, and some of multi-agent reinforcement learning algorithms even show superhuman-level performance in some multi-agent games, such as Dota 2 and StarCraft. However, most of multi-agent reinforcement learning algorithms operate on low-dimensional observations, such as grid world-like environments or gaming environments. For embodied systems, although there are some high-performance 3D simulators and numerous large-scale visually rich 3D datasets are proposed, most of them do not support multi-agent siting. Therefore, there still exists a huge gap between multi-agent system and perception in realistic visual environments. To close this gap, we introduce a collaborative visual navigation task for image goal-based multi-agent navigation under very realistic 3D environments. In this task, we assume there are a group of agents situated in an unknown environment, and each agent is to navigate to a target location indicated by a goal image under a cooperative setting. This agent perceive the environment from their own view, but they can exchange information via a low bandwidth communication channel. Moreover, to cover more challenges in multi-agent systems, we consider 3 different task settings. First, common goal. In this task, a group of agents are assigned a same goal picture. Second, specific goal, where different agents are assigned different goal pictures. Third, ad hoc cooperation. In this subtask, the numbers of agents in the training stage and the test stage are different. Basically, common goal serves as a basic setting where agents learn how to cooperate to reach a single position faster. Specific goal addresses a more complex situation where agents need to cooperate with individual targets. Ad hoc cooperation addresses a more open world setting. This task is also built upon common goal. That means agents also share a same goal picture, but it requires agents to adapt to different team size. Different from common goal and specific goal, where the agents learn a fixed and team-dependent policy in close multi-agent reinforcement learning environments. Ad hoc setting require agents to learn some more flexible collaboration policy, which can be adaptive to different team size during deployment. We further develop a corresponding data set. Our data set is built upon Gibson. Besides inheriting the advantages of iGibson, such as high quality rendering, rich visual diversity, and good accessibility, our dataset has some unique characteristics. First, it supports multi-agent operation. Our dataset supports multi-agent visual navigation with arbitrary group size. By accounting for different constraints of space and physics, such as occlusion, gravity, and so on, the agents can be safely initialized. Moreover, all the 3 task variations mentioned before are involved in our dataset, and they are combined with a package of evaluation tools. Further, our agent also allows flexible target generation. Our dataset can generate different target pictures flexible. It will support the 3 task sightings and the future dataset extension. And our dataset can also allow efficient paranomic rendering. A rendering engine is equipped to offer agents egocentric panorama in real time. Our engine is well optimized on GPU, greatly speeding up multi-agent training. It is much faster than iGibson's engine. In this table, we give some detailed comparison to previous embodied navigation tasks and data sites. And here are some statistics about our proposed dataset. With our proposed dataset, we further develop a memory-augmented communication method for multi-agent visual navigation. Basically, existing multi-agent reinforcement learning algorithms can be classified into 4 different classes. For the first type methods, they focus on analyzing the behavior of single-agent reinforcement learning algorithms in multi-agent environments. For the first type of methods, they address collaboration through implicit communication, which attracts increasing attention recently. For the third type of method, they indirectly achieve cooperation by using policy parameter sharing strategy, for example. And there are also some other methods try to build models to reason the behaviors of other agents for better decision making. We specifically focus on explicit communication. Communication is viewed as an efficient way of multi-agent interaction. Communication is especially crucial when a set of cooperative agents are placed in partially observable environments, like our setting. The agents need to exchange information, coordinate their actions, and achieve the goal better. So, for communication learning, existing methods propose many different communication structures, like fully connected star tree, neighboring hierarchical structures, for facilitating training and information exchange. Different from previous methods, we address information storage and reuse during communication. This is achieved by a memory-augmented communication method. Here we give a brief illustration of our model. Specifically, each agent has 2 key components. The first one is a map building module. This model is to infer the environmental representation for path planning. And the second one is a memory augmented communication module. It gathers information from other agents. Moreover, this model is equipped with a private memory for information storing and recording. For communication, we adopt a widely used handshake communication strategy. It contains 3 stages: request, match, and select. For the request stage, at the beginning of each communication step, each agent first comprises its local observation to a query, key, and value. Then this agent will broadcast the query to other agents. As the query vector is a small size, this only causes little bandwidth transmission. Then, in the match stage, every other agent will derive a matching score between the received query and its own key. This matching score can be intuitively understood as the importance of the information provided by the supporter for the requester. Finally, in the connected stage, the requester will select some agents to build a temporal connection according to the matching score. And the requester will gather information from these temporally connected agents, weighted by the matching score. The gathered information will be summed together and used to support decision making. In handshake communication, all the information are directly bounded after each connection stage. So this is problematic, as a bounded information might be of great value in the future. The communication is mainly about agents' current observations, failing to explicitly involving their past parents. It is difficult if an agent wants to know other agent's status in a previous time step. So this easily leads to suboptimal short-sighted behaviors. To address these limitations, in our approach, we let each agent maintain a private memory, which stores all its past gathered communication information. Thus, the agent can safely store, accurately recall, and efficiently exchange its past experience. In each round of communication, each agent can send a more reasonable request to other agents by considering both its current state and stored information. And each of other agents will check both its observation and memory to give a better feedback. Thus, the agents can conduct more efficient communication by sharing not only their current perceptions, but also their historical experience. In this way, agents' decisions depend not only upon their current status, but also upon their collective long-term experience. For multi-agent policy learning, we adopt an actor-critical model and consider it under a fully decentralized multi-agent reinforcement learning setting. In standard actor-critical models, an actor proposes an action, and a critic gives a feedback accordingly. Proximal policy optimization utilizes neural networks to approximate the actor as a policy function and the critic as a value function. And these loss functions are computed for policy learning. As these loss functions do not involve any cross-agent interaction, policies are just learned independently. To address this issue, many multi-agent reinforcement learning methods train multiple interacting agents in a centralized training and decentralized exhaustion manner. They learn decentralized policies with a centralized critic. This critic can collect all the observations to estimate a joint state of all the agents. However, as our communication learning method is essentially under a fully centralized setting, agents can exchange information via a time-varying communication network. We therefore learn an individual value function for each agent, depending on their local observation and received message. For performance benchmarking, we can consider three competitors. The first one is IPPO. It learns target-driven multi-agent reinforcement learning policy. Instead of using communication, IPPO accounts for other agents' actions using independent PPO algorithm. And the second one is MAPPO. It learns a centralized value function that conditions on the collections of agent observations and a decentralized policy based on local observation using multi-agent PPO. And the third one is the handshake communication strategy, which has been mentioned before. From these three tables, we can first find that our method outperforms other three competitors over all the three multi-agent visual navigation settings across almost all the metrics. Second, we also observe the performance gap between our algorithm and other competitors becomes more significant with the increase of the team size. Last, we can also find the distance navigation is quite challenging for all the methods, but our model still performs relatively better. We also conduct a set of ability studies. From this table, we can find that map building module and the memory augmented communication module indeed boost the navigation performance. Moreover, the memory mechanism can significantly save bandwidth usage. So these ability studies will verify the effectiveness of our current ideas. This figure also intuitively demonstrates the benefit of collaboration. In the top image, there are two interacting agents. With their collaboration, they can successfully reach the target location. While in the bottom picture, there is only a single agent without help of other agents. This agent stops at the wrong location. Okay, that's all I have for today. Let me now summarize what I talked about. I first addressed the importance of active perception and present a strong vision language navigation agent that can make exploration for information gathering and better navigation decision support. Second, I talked about long-term planning. By building a structured semantic, long-term reasoning can be conducted over the global action space, and the navigation performance can be significantly improved. Finally, I present our recent work on multi-agent collaborative navigation. Toward this direction, we build a large-scale dataset and propose a memory-augmented communication model. Thank you so much for your listening.
Okay. Now let's take a 5 minutes coffee break. And Wen Guanwang is not here, and he will join our workshop soon. So let's put the QA part together with the Professor Batra. So let's take a 5-minute coffee break, and our workshop will be continued after 5 minutes.
Finger, do you want me to get started?
Yeah. Now we are glad to invite the Professor Batra to share his works.
Okay. Thanks, everyone, and thank you to the workshop organizers for having me. It's a bit early on the West Coast, so if I seem a bit groggy, that's because it's it's a bit early, body clock time. What I want to talk to you today about Habitat 2 is Habitat 2.0. This is this line of work that we've been doing for the last 2 years. We published Habitat simulation platform at ICB 2019, where we were fortunate enough to be nominated for the Best Paper Award there. For the last 2 years, we've been working on making a transition from navigation, which was the focus of Habitat 1.0, to mobile manipulation, which is the focus of Habitat 2.0, and it's appearing at NeurIPS this year. So before I dive into Habitat 2.0, let's just quickly recap what we understand about Habitat 1.0. This was a large effort. It's a multi-year, multidisciplinary, multi-institution collaborative effort between a large group of people. We've been building a simulation platform for embodied AI research. Our goal is to create the ImageNet, the COCO, the VQA equivalent of embodied AI, meaning that we want to converge on what is the right data set, what is the right simulator, what is the right task, what is the right benchmark challenge to make progress on some of the problems that we want to solve. And we think about the abstraction of embodied AI problems space at 3 levels in a stack. At the bottom are 3D assets. In the middle are capabilities that a simulator may have. And at the top are tasks that are studied in embodied AI. So let me walk you through what kinds of assets we were using in Habitat 1.0. And the short answer is that they were primarily 3D scans of indoor environments, or 3D place data sets. These are data sets like Matterport 3D that contains 90 multi-floor house reconstructions, or Replica, which contains 18 near photorealistic rooms, Gibson, which has a large number but lower quality reconstructions, or ScanNet. This is one such fly-through through a reconstruction of a multi-story house in the Replica dataset. You can see that the reconstructions aren't perfect. Sometimes thin, long structures do actually have geometry errors, but they're extremely high quality, with every single object also annotated with its semantic ID, meaning that we can render RGB, depth, instance, and semantic segmentations from arbitrary views in these reconstructions. And this can really drive progress in computer vision in a way that is hard to do with static data sets. What we can also do is now bring our own scans. So this is a device called the Matterport scanner. That's my student Joanne Truong, placing it at various locations. It captures an RGBD point cloud at various locations, uploaded to Matterport servers. We can download a 3D scan that can then be used with Habitat Simulator to conduct experiments in simulation in a real space. Simulation of a scan of a real space. And more recently, this is also appearing at NeurIPS dataset and benchmark track. We have released a dataset called the Habitat Matterport 3D dataset in collaboration with Matterport. It is a dataset of 1,000 building level scans. This is the largest dataset of 3D scans out there. And so far, as I mentioned, the scans in literature were either small and high quality, or numerous but then low quality. HM3D really tries to push the boundary on both fronts. So this is, for example, what an agent navigating in Habitat in a HM3D scan looks like. You'll notice that the reconstruction quality is, again, not perfect, but it is extremely high quality. It is much higher than some of the Gibson scans or other data sets available. HM3D has 1,000 indoor scenes, which is an order of magnitude more than MP3D dataset. It's split into 800 train, 100 val, and 100 test houses. So really now we're getting to the kinds of numbers that we can have confidence in our methods on. There are 50 empty unfurnished homes, which can be in simulation. New objects can be inserted there, but 950 of them are furnished houses. And they've been manually vetted for reconstruction quality by a team of annotators. We are also working on semantic annotations for HM3D. So we're working on annotating every single wall, floor, object, every triangle, every mesh in the 1000 scans with semantic IDs. This is an extremely large scale and expensive and massive undertaking. So this will take a significant amount of time and effort. But I wanted to give people a heads up that this is coming. This is not public yet. This is not part of the release, but this should be coming sometime in the next year. And just a quick check of statistics. As I mentioned, most data sets are small. In contrast, tens or hundreds of scans. Gibson does have 571 scans in the dataset, but if you do a manual annotation of the quality of those scans, most papers only use scans with annotation quality 4+, and then there's only 100 of them. ScanNet has a significantly larger number, but those are single room reconstructions. So if you look at the floor plan space, that's significantly smaller. So that's the so in that sense, it's very clear that HM3D is an order of magnitude larger than most of these existing data sets. So that's at the bottom level of the stack, 3D assets. Now talking about what sort of simulation capabilities did we study in Habitat 1.0? Our focus primarily was navigation. So in terms of simulation, we actually decided that we would not do rigid body physics or deformables or anything else. It was just navigation. There was a pre-computed navigation mesh on the floor that the robot could navigate on. It still means it's continuous navigation, but it means that you don't have to solve collision checking. The only thing you need to simulate is rendering. So egocentric RGB, depth, semantics, and localization and so on. The kinds of problems we studied were point goal navigation or object goal navigation, where the name of an object is given, or room goal navigation, where the name of a room is given to the robot, or VLN, vision and language navigation, where a full instruction is given, like turn around, go to the bathroom, turn right, or embodied question answering, where the agent is asked a question and has to explore. Our key engineering contribution in Habitat 1.0, that this was over 50x faster than anything else available at the time. So we were comparing to an earlier version of Gibson, AI to Thor, Minos, House 3D. They were in the tens to 100 step frames per second of how many frames of egocentric observations they could generate in 1 second of wall clock time. Habitat is a few thousand, and when processed multi-process on a single GPU can go over 10,000 steps per second. So that gives you an order of magnitude comparison between the various simulators. And what we had also shown in a paper called DDPPO that appeared at iClear in 2020 was that we could really scale learning and essentially achieve near perfect or saturated performance on a data set, on a held out data set, by really scaling learning to 2.5 billion steps of experience, which is over 80 years of robot simulation, of robot experience time, in 180 GPU days done with 64 GPUs on 3 wall clock days. So there's just extremely large scale experimentation here. But we essentially found that this problem of point goal navigation with noise-free depth and ego motion sensing is essentially fully learnable. Not only that, we found that the sim to real transfer essentially works. So we could take an indoor space, we could scan it, we could conduct identical studies in simulation and reality. So that's what I was showing you about scanning spaces. We compared multiple methods. We compared their simulation performance to how those methods perform on the real robot in that real space through multiple episodes, multiple room rearrangements. And we essentially find that there's high degree of correlation. There's high predictivity between the simulation and reality results, suggesting that when we run a competition in simulation, improvement or progress in simulation is predictive of progress in reality, which is very heartening and good to know. Okay. And there's been for the last 3 years or so an annual workshop on this called the Embodied AI workshop at CVPR. We've been organizing a competition initially just on point goal navigation, but most recently also on object goal navigation. And it's been it's a fairly healthy community. The number of teams has been growing, the number of submissions has been generally going up. And correspondingly, the state of the art has been going up on point goal navigation without any localization sensor. The state of the art in 2019 was somewhere around 15% success. And this year, the winning entry is 96% success. So this data set is also getting saturated, which means that we can now take on more challenging problems. Okay, so that was a quick recap of Habitat 1.0. As I mentioned, the emphasis in Habitat 2.0 is to transition from navigation to mobile manipulation. And so we are imagining indoor home assistant robots like the kind shown here. This is a mobile manipulator called Fetch. It is navigating, opening a drawer, picking up an object, then navigating in, putting that object down on the table. So you can imagine this is solving the sort of home assistant tasks like go fetch me this object, clear the table, put the dishes in the dishwasher, put the dishes in the sink, clear my refrigerator, throw out things or things like that. The common home assistant tasks that we would like robots to be able to do. The paper is appearing at NeurIPS this year, as I mentioned. It is again a collaborative effort with a large group of collaborators and a large team with a fairly diverse set of skill sets. We have experts in computer graphics, in machine learning, in rigid body physics, in other just systems, and also robotics. So the ingredients, how do we get there? How do we build large scale simulators where we can study these home assistant tasks? That's what I want to tell you about today. And again, I will go through this in that same 3 level of abstraction. So let's start with what is the task that we want these home assistant robots to solve. The most simplest tasks that you've seen in other simulators and other efforts as well is what is called the pick task. So you take a manipulator. It can be a mobile manipulator, but you may have also seen it with a fixed base manipulator. In this case, we picked a mobile manipulator for easy generalization to other tasks. So this is a Fetch robot. It's a commercial platform, readily available. We did not do any sim to real transfer in this work, but we are thinking long term about it. That's why we chose an existing hardware platform. Fetch is equipped with 2 onboard cameras. One is mounted on its quote unquote head. The other is not visually shown, but it's mounted on the arm. These 2 visual sensors are also augmented with proprioceptive sensors that tell the robot where its base is, where the arm angles are with respect to the body and so on. And the task is for the robot to reach out, pick an object given the coordinates of that object, and retrieve the arm back to the stable position. One simplification that I don't know if people caught it, but I'll play this video again. And what I want you to notice is that the gripper, even though it's visually depicted as a parallel jaw gripper, it's actually a suction gripper. So as soon as the end effector gets close to an object, the suction gripper basically attaches the object into the grip. This is a task level simplification, not a simulator level simplification. We have done experiments with parallel jaw, rigid body physics. This is just we want to put grasping outside the scope of the problems that we study initially, and then we think this will be expanded in later years. The task is successful if the robot picks up the right object as specified by the center of the mass. of the object, it returns the arm to the stable position, and there is it doesn't exceed a collision threshold, so it doesn't collide its arm against other objects or obstacles in the environment. So these sorts of pick tasks and reach tasks are studied in the literature a lot. So there is the OpenAI Gym fetch reach environment as well, or the fetch pick environment, or the fetch push environment. There's a Franca kitchen environment that is used in relay policy learning and other papers. I think in contrast, the biggest difference in our work is that is A, photorealism. So you can notice the visuals are very different. And B, just that there is an actual indoor environment. So in the OpenAI Gym environments, the base can't go anywhere. There's no other environment around it. And in the Franca Kitchen environment either, there's just nowhere to go. There's nothing else in the environment. Here, there's a full house, which I'll talk about. So this is just the starting point, but there are much more challenging tasks that we study. There's this tidy of the house task, which involves moving 5 objects from their start locations to goal locations. So this is what that looks like. The robot has to go pick up object 1, put it in its right place, navigate again, pick up object 2, navigate, put it in the right place. So notice this is what I mean by there's an actual house, right? There's a space. There's not just a kitchen floating in the middle of nowhere. We also study this task of preparing groceries, which involves picking object 1 from the fridge, putting it on the counter, picking object 2 from the fridge, putting it on the table, picking object 3 from the counter and taking it to the fridge. So there are containers here. Those containers are open. The robot does not have to open the containers. And finally, there's a set table task that involves opening of those containers. So there's a bowl that has to be picked up from the drawer. Then the drawer has to be closed. Then an apple has to be picked up from the refrigerator, and that has to be put inside the bowl on the table. And then the refrigerator door has to be closed. So this is a much more challenging task because you have to interact with articulated objects like drawers and refrigerators, and you have to close those objects, open and close them. The goal specification in all of these tasks, whether it's pick or set table or prepare groceries or tidy house, is what is known as geometric goal specification. So there is a start state, S0, where we know the center of masses of certain objects. We know nothing else about the environment. The robot does not have a map, does not have obstacles, does not have supporting relationships, does not have names of objects, nothing. And there are goal center of mass coordinates. So if you want the Cheez-It box, for example, to be picked up from the table and placed on the sofa, you have to give center of mass coordinates in the robot coordinate frame of the start and the end. I want to highlight that center of mass is a fairly weak sort of information. Notice that at the start position, if the object is inside receptacle, so if the apple is inside the fridge, this has to be sensed that the apple cannot directly be reached. The fact that the refrigerator door is closed is not told to the robot. You have to sense it. If the drawer is closed, this has to be sensed. The robot just knows the relative coordinate of these objects. And when you need to put objects one on top of the other, you're given coordinates of the center of mass, but you don't know if those are stable positions. So you have to figure out that the bowl needs to be placed first and then the apple inside the bowl. Otherwise, the bowl will just roll away and things like that. So center of mass feels like it's a lot of information, but it's not a lot of information. There's a lot of sensing that still has to be done. This follows the recommendations from a tech report that we released last year. It's called Object Rearrangement, a Challenge for Embodied AI. This was with this group of researchers listed here, where we essentially formulated generalized rigid body rearrangement as a problem, which involves representing the world in some as a piecewise as a composition of piecewise rigid objects and converting it from a start state to a goal state. And we said that is a problem that we should study. It has broad systematic use across a number of applications. And we said the key limiting assumptions are is the world is made of piecewise rigid objects, and the robot does not have access to the world state. No pre-computed maps, no knowledge of 3D objects, no logical state abstractions like no abstraction that says find object or like A is on top of B. Like you just don't have sensing. You have to sense it from cameras, and no magical sensing of physical parameters. Like you don't suddenly get to know masses of objects or their physical properties like friction. You have to interact with the world to figure that out. What is out of scope is there's no non-rigid dynamics. There are no deformable objects, liquids, films, clothes, ropes. There are no physical transformations. So objects start as piecewise rigid and they stay piecewise rigid. Objects cannot be melted. You cannot attach objects to each other. There's no soldering, there's no welding, there's no cutting, there's no drilling, there's no sanding. So you cannot break things, you cannot attach things. Things start as piecewise rigid and they stay piecewise rigid. And in some sense, the robot is provided a goal specification, not the full state abstraction. So the starting state is S0. The robot only has access to an observation through its cameras and sensors. The ending state S star, the robot is told about it through a goal specification. It does not have access to S star. The goal specification can be done through a number of ways, like the geometric goal that I mentioned, but also language goal. I can tell the robot, move the toaster next to the coffee cup, or I can give an image of what I want the final configuration to look like, or something known as an episodic memory goal, where the robot can experience what the clean state of the house was that it has to be returned into. These are all different specifications. We use the geometric goal specification, as I mentioned, and that's what I'll stick to for the rest of this talk. So that was the task. I think the next thing that we have to immediately address is, where do these 3D assets come from that I've been showing you? So this space that I've been showing you is an actual apartment, and this is a scan of that apartment in the replica dataset that was released in 2019. This dataset is extremely high quality reconstructions, high fidelity, but it is ultimately a static 3D mesh. These objects cannot be picked up. The inside of cabinets was never scanned, so that's not visible. The cabinets cannot be opened. So this is just a giant static 3D mesh, which is good for rendering, but not for interaction. And so what we did was that we hired a team of 3D artists to take every object in the scan and convert it into an interactive CAD asset. Sometimes that would require making editorial judgments and hallucinating details. So if the fridge was closed in the scan, an artist has to hallucinate what the inside of the fridge might look like. And ultimately they did this for the entire apartment. So on the left is again the scan. On the right is a reconstruction of the scan from CAD objects, interactive CAD objects. So you'll notice that it is quite faithful. It is obviously not perfect, but it is quite faithful. And there's been an attempt made to reconstruct it to the degree possible. And every single object on the right can be picked up. The drawers can be opened. So the spaces are fully interactive, right? The drawers can be opened, new objects can be there, cabinets can be opened. And this conversion of a scan into a reconstructive asset, into an interactive CAD model, allows us to then study interaction tasks in these spaces. It also allows us to create what we call macro variations. So we can take those same assets and move, floor plans around. So we can change where the kitchen is in the house and where the living room is in the house, and also micro variations where we just move furniture around. We don't change major layouts, but we just move furniture around. There are about 90 objects that were constructed, everything from kitchen utensils to books to TV stands and sofa, and there are a different number of occurrences of these objects. This is because we are faithfully trying to recreate a scan, which itself is a capture of a real space to the degree possible. This has the same statistics as that real space. We've also annotated tables and other surfaces with supporting relationships about where objects can be supported. And so there's a process to do procedural clutter generation. So objects from replica CAD and also from YCB dataset can be inserted into these supporting relationships so that we can generate clutter in a programmatic manner as needed. And we can do large-scale reinforcement learning. So picking up objects from various kinds of objects from various kinds of receptacles in these environments. But more importantly, we can do systematic generalization. We can study how effective these policies are in picking unseen objects that they've never seen during training, or unseen receptacles. So on the top row are the training receptacles that the robot has been trained to pick objects up from. And on the bottom row are the testing receptacles that it has never seen. It's never learned to pick up an object from those receptacles. Or we can also do generalization to new layouts. So on the left is one particular layout of the house, and the right is another particular layout of the house. In both of them, the robot is picking up a known object from a known receptacle, but the house has been laid out differently. Therefore, it plays a role in navigation problems and where the robot stops and what sort of clutter might be around it and so on. So those were the assets. Let me quickly mention what goes into the simulator capabilities. So as I said, the key thing here is piecewise rigid body physics. We relied on Bullet Physics Engine, which is a fantastic effort led by Erwin Koumans at Google for over a decade. It's an open source physics engine that we integrated with Habitat, and that serves as our backbone here. Our main contributions are in making sure that the entire simulation framework runs fast enough. So for us, a step, we'll do benchmarking via this notion of steps per second. And for us, a step is a rendering pass that renders images, and 4 physics steps, each simulating 1/120th of a second. This is a fairly standard configuration that allows for 120 Hertz control and rendering of images. These numbers have been chosen such that 30 steps per wall clock second would be real time, would be considered real time. So that's our benchmarking number. 30 steps per second is it would be considered good. If anything faster is faster than real time, anything slower is slower than real time. Most existing simulators like RLBench, AI2Thor, iGibson, 3D World, and Sapien are something in the 10 to a few hundred steps per second range. Habitat 2.0 single process runs at over 1200 steps per second, which is 3 times faster than anything else available and 47 times faster than real time. But we can run multiple instances of the simulator on a single GPU, and we can increase throughput of the frames and the observations generated for reinforcement learning. And that is over, roughly 8,500 steps per second, which is 30 times faster than anything else and 280 times real time. And of course, we can also scale this to multi-GPU settings on a single node. And that's at 25,000 steps per second, which is 100x faster than anything else and 850x real time. And this scaling really matters. This speed really matters because in our paper, we ran experiments. So if we count cumulatively the steps of simulation that went into all the experiments that went in the paper, but excluding all the iterations that we did to build up to the paper, none of that, just the experiments in the paper, they sum up to 6.6 billion steps of simulation. And simulating that in Habitat was less than 3 days. Simulating that in anything else would have taken us 295 days. So basically, this paper just wouldn't be possible if we had to do it in another simulator. So that's the simulation. Now let me talk about, now that I've told you about the task, the simulator, the 3D assets, the question that I can answer is, so what did we learn from all these experiments? Well, we compared 2 different classes of methods. The first one is this broad class of monolithic neural networks trained with end-to-end reinforcement learning. By monolithic, I mean, we just take all our sensory observations, the head camera, the arm-mounted camera, the depth image RGB, stack them into a visual encoder like a ResNet in our case, take the proprioceptive sensors, the robot state, like the end effector, the arm position, the base position, the object goal states, and the start states, have a state encoder, and we just send that to an LSTM to output certain actions and value estimates. The actions are controlling the base through linear and angular velocity. They are controlling the gripper by specifying that it should grasp something if it's close to an object, and an end effector displacement. So this is end effector control. So we just tell the robot basically tells the end effector to move in a 3-degree freedom space. This monolithic neural network can be trained for the entire task of like rearranging a house, or what we can do is we can couple it, or we can use it to just train a skill like navigation or picking up an object, closing a drawer, opening a drawer, and then we can chain those skills together through a task planner that first calls the navigate skill, then pick skill, then play skill, and so on. So this is one class of methods. We also compared to classical sense plan act pipelines from classical robotics. So this involves sensing the environment through an RGBD camera to construct point clouds in the world. Finally, it involves performing planning in the configuration space. So the 7-degree of freedom arm and the base if we are navigating as well. So there's planning in this space to avoid collisions with the point cloud that has been constructed, and ultimately acting via a controller that actually executes that plan through an actual controller. And this can also be coupled with a task planner. So sense plan act can be done for just the pick skill or some other skills, and a task planner can chain them together. So as I said, we trained the skills, the reinforcement learning skills on a large number of environments. We did systematic generalization to unseen objects, unseen layouts, unseen receptacles, and unseen layouts. And this table summarizes our findings just on the picking task, and I'll tell you about results on the full tasks. So on the picking task, just end-to-end monolithic neural networks trained with RL versus sense plan act. These are the seen results, success rates, and these are the unseen success rates. And some of the key trends that we find are obviously on the seen examples, learning will outperform sense plan act because you can essentially memorize. But what's interesting that is on unseen layouts, so new house layouts, learning still outperforms sense plan act pipelines. On unseen objects, learning is about the same as sense plan act pipelines. On unseen receptacles, learning is underperforming sense plan act pipelines. And we think that if we look at our data set, it becomes clear why that may be the case. So the evaluation of unseen receptacles, there are tight spaces that are very different from the spaces in training. We think these trends will change if we had access to more data, more kinds of 3D assets and receptacles. Here are what the results look like on the full task. So on the right, I'll play a video. I'm showing you a particular baseline, which is task planning coupled with skills trained with RL. On the y-axis is success of how it succeeds. On the x-axis is interactions. So I'll play this and I'll walk you through it. Basically, this task involves navigation, picking, navigation, placing, navigation, picking, and so on. So it just repeats between nav, pick, nav, place, nav, pick, nav, place. That's what this arrow is showing. The arrow indicates navigation, pick indicates the interaction, navigation, place, and so on. So there's nav, pick, nav, place on this thing. So on the x-axis are the number of interactions that are happening with the environment, and we are not showing navigation as an interaction. So it's just a step along the way. And the blue line is what we're focusing on. And what we notice is that, even if we can do navigation well, which is what the navigation community is studying, and then we can do some picking, we're at roughly like 70% success. But there are just cascaded errors. It becomes worse and worse as we run this longer and longer. And by the time you have to move 5 objects, you're essentially at 0% success. We have done large-scale studies of multiple methods, monolithic RL, task planning, and so on. And essentially all methods are in this regime of they're all failing. We've also done studies where so these dashed and highlighted lines are the ones where we couple them with Oracle navigation methods, and so they're much better because navigation is the most commonly used skill in these environments. Well, some of the problems that we see is that just monolithic RL for the entire task just fails to learn. If you have to control the base and you have to control the arm and you have to move 10 objects around, we just couldn't get it to do anything sensible. We also see pipeline approaches suffer from handoff problems. So here what happened is that navigation was called, then it was stopped, and then the next skill was close the drawer, but it stopped too far from the drawer that it couldn't reach that drawer. Here's another example where navigation was called, then picking skill was called, then navigation was called, but again, the robot stops at a place where it can't actually place it. So the target for placement was here, and it stopped too far. And so anytime there are these cascaded methods, you suffer from these sorts of problems. So the key takeaways for us, the learnings were flat policies really struggle, whether they be sense plan act or learning based. Hierarchical approaches are really necessary for long horizon problems. But hierarchical approaches suffer from handoff problems. You have just these cascaded errors that build up. And sense plan act pipelines are generally brittle compared to RL methods to these handoff problems. So I'll conclude here. In conclusion, with this work, we introduced replica CAD, which are these environments of interactive 3D assets for indoor home environments. We introduced Habitat 2.0, which is a fast physics-enabled photorealistic simulator. We did a lot of systematic analysis of the picking task, and I encourage you to read the paper. There's a lot more analysis in there. And finally, we are built up towards a home assistant benchmark where robot navigates, picks up, and interacts with objects in the environment. Overall, we think these are the sort of problems that may be the next generation of intelligent systems that we should build towards. Okay, I'll stop there.
Okay, thanks, Dr. Wang and Professor Durabatra. Now is the question time. Is anybody have some questions?
Yeah, for now I have some questions. Can I ask now?
Yeah.
Yeah, so thanks so much. So first, thanks, Rolf. So yeah, thanks so much for providing so many data sets and simulators. So my first question is, well, in Habitat 1.0, you actually showed us a same to real case, but in that case, I mean, the simulated environment and the real environment are identical, right? So, and there are not lots of rich visual features. I guess the visual information received from the real robot sensor might be very similar to the visual features received by the agent in the simulator. So, I mean, is this a really challenging task? Is that possible? I mean, to train the agent in the multiple 3D simulator, but test it in a real multiple 3D environment? Is that possible, or is that hard?
Yeah, actually, that is what we did, right? So when I was showing you the results of that space, let me see. I can share my screen again. Yeah. Okay, so this screen, when I was talking about this. So when we are talking about sim to real transfer, we actually do not train in the simulation of this space. So these policies were trained in scans of Matterport environments, and all we are doing is testing in this space in simulation and testing in this space in reality. Because what we're interested in establishing is, in a new space, what does the simulator say your accuracy will be, and what do you observe as accuracy in reality? So all of these methods that are shown as dots on this axis are actually navigation techniques that have been trained on Matterport scans and Gibson scans and are being deployed in this new space. They have not been trained on this new space.
I see. So you train them on the Matterport 3D simulator, but test it on two scenarios: one scenario in simulator, one scenario in real environment.
Exactly.
Exactly the same. Okay, I got it. Sorry. So the second question is, I mean, for the sim to real, I think it's very important. I think that's actually the future of the visual navigation, even for the visual language navigation. But how can we test it? We train for the simulator. We can test it or we can compare the methods fairly, but you know, on the real environment, it's very hard to test, right? So how can we do that? So do you have any comments or suggestions for that?
Yeah, I agree. It's hard. I think this is why simulators will play an increasing role in making sure that we can do systematic comparison. I'm tracking some efforts from so the iGibson folks in 2020 and the AI to Thor team in 2020 were trying to conduct these challenges where they would ask participants to participate in a competition. If the top 5 methods from simulation, they would run it in real spaces. So I think those may be directions in which in which people can run competitions where a small set of approaches are tested on hardware. The robotics community does this regularly. So, you know, at ICRA and IROS, there are often these competitions where, you know, on the fetch robot, they will run those hardware competitions. But I think fundamentally, I think when the computer vision community reports results on COCO or ImageNet or Pascal or any of these other data sets, we have growing confidence that when progress gets made there, ultimately that progress shows up in products downstream. We don't all simultaneously have to working on that product in order to believe that our methods are making progress. I view embodied AI the same way. We will, once we are fairly confident that progress in simulators is correlated to progress in reality, the burden will not be on every single CVPR paper to conduct a robotics experiment, just like the burden is not on every single CVPR paper to show an actual camera product. And
I agree.
Yeah.
Thank you very much. Thanks for the comments. Yeah, thank you. So my second question is for the Wenguan. So for the collaborative navigation task, my question is whether these collaborations are really necessary. So it looks like all the tasks in the proposed data set can be done by a single agent, right? So my question is, did you show the performance or the successful rate if you only have one agent for these tasks you proposed in the collaborative navigation data set?
Yes, we have observed that with the help of the communication, multi-agent can reach the target more faster and gain improved successful rate. So this shows the advantages of collaboration. And for the collaborative navigation, I think the specific task setting is not that important, but we just want to show that the agents can learn some collaboration behavior like human beings, but we just put this our focus on a specific task in our case. Yeah.
Okay, thank you. Got it. Okay, I have no more questions.
And for your previous question about the simulation to real, I also noticed that there are some works in this direction, and some methods they just try, for example, train an agent in a simulator A, and then test the performance of this robot in a simulator B. So they just use this kind of case to simulate the simulation to real environment. So that means we do not need to really deploy the robot in the physical world, but we just use 2 different kind of simulating environment. And
so it's not on-scene environment, but on-scene simulator, right?
Yeah, exactly. So they can easily test the generation ability of their algorithm. Yeah, maybe this is a cheap way. Yeah.
Okay, I see. Thank you very much.
Yifeng, please.
Hello, Professor Bertrand. I have a question for this using the simulator actually. So, well, first of all, it's very impressive to hear about Habitat 2.0. I think it's very exciting work for future research. But I also noticed that studied that kind of problem, and especially when you use RL in that complicated environment, usually requires a huge amount of hardware, right? I found that for example, in your work, DDPPO and the new ICCV waypoint models, they both use something like 64 GPUs. So I'm wondering if for example, for a group that doesn't have that much computational resources, it's still possible for us to have a chance to study those interesting problems. And what our direction should we go? Thanks.
Yeah, thank you. That's an important question. Thank you for the kind words about the work. I completely agree with you. I would feel very disappointed if the only people who could contribute to this research were the ones who had access to large clusters, because then I feel large parts of the world, like my own lab at Georgia Tech, wouldn't be able to contribute because they don't have access to that large a cluster. So I think I view some of these papers as existence proofs, that they come along and they show something is possible once, and then much more efficient techniques develop that make it possible for to train it faster. So in the point goal navigation case, DDPPO showed that it can be done. The problem is entirely learnable. And then we did a follow-up work with Joel Yee at Georgia Tech, who showed that auxiliary tasks help in sample efficiency. And so then you don't need to train it to 1 billion steps. You can do it in a couple of, tens of millions or so on. And so then they were able to run those experiments on, 4 to 8 GPUs. Yes, it's still not 1, but it's at least lower. And I think as we make simulators faster, it's going to reduce the computational burden on how many GPUs you need. And the other thing is that I do think that we do need to invent more sample efficient methods. Right now, we are relying on methods that are just doing random exploration. Like there is just the chance that you will randomly move your base and your arm and open a drawer is just so low that you have to scale these methods out to billions of steps. But I think imitation learning has a lot to offer, getting demonstrations from humans using hierarchical methods. So I completely agree with you. I think scale right now is a band-aid, and we will have to get away from that scale eventually.
Cool, thanks. And I also have a question for Dr. Wang. So
Hi.
I'm quite interested in the work that you presented related to like structured memory or backtracking, exploration. So I have a question so during training at the early stage, especially, I think that things like backtracking or exploration is can always happen because the agent makes lots of mistakes at early stage of training. But as it goes further at the later stage, the agent is less likely to make mistakes, especially in Matterport 3D. I found that in lots of VLN agents in Matterport, those network overfits severely, right, at the later stage of training. So I'm wondering if those exploration method or backtracking method is still useful at the later stage, and if those are not happen as frequently as in the early stage, wouldn't the model forget about what they have learned about how to do exploration or how to do backtracking? Yeah.
Okay.
Thanks.
Yeah. The backtracking is try to correct some wrong decisions, right? So previously in our active exploration work, we just think that such kind of wrong decision, a large part of this wrong decision is caused by the ambiguity of the limited perceptual field. So we try to enlarge the perceptual field. We just let the agent to make furthermore a large range exploration. The agent can explore its surroundings, so the agent can gather more information. Thus, they can avoid to make some mistake decision. Yeah, but from a more insightful view, the reason for that it's very difficult to let the agent to make some backtrack. This is because the agent is only limited to its local observation. So the action space is very limited. It just make decision around his current observation, but he cannot easily reach the previously visited place. So I think in the from a more fundamental point, we should let the agent put his decision over the global decision space. That means he needed to memory all the related points and then make a decision. Thus, they don't need to use some heuristic strategy to backtrack. Instead, he just make a decision, or I need to revisit a previous related location. So this decision can be a part of learning instead of some heuristic strategy. So I think, yeah, in this way we can either make the training more easily. So that's why we use the memory, or we can. It's also a kind of map building strategy.
Yeah, thanks. But I understand it will be very helpful in training, but during inference, does that happen very often? Like, right. Okay, cool. Thanks.
Okay. Thanks again for Dr. Wang and Professor Bertrand. We have an impressive discussion. Due to the time limit, we should move on. Next, we are glad to invite Professor Wu from the University of Adelaide to share his works.
Hi, Fonda, can you play the recorded videos? My connection is not stable.
Okay, okay.
I will answer questions. Hello, everyone. Thanks for the invitation of this human interaction for robotic navigation workshop. I'm Chi Wu from the University of Adelaide. Today, I will talk about the vision and language navigation. So to introduce VLN, we need to first talk about the vision and language, more precisely, computer vision and natural language processing. Well, computer vision and natural language processing are two independent research areas, but since 2015, there is a trend that tries to combine vision and language. So integrating language with vision actually expands the horizons and the tasks of the both vision and language community. For example, combining the image understanding task in the computer vision and the task of language generation in the NLP makes the image captioning problem. We also can combine several general computer vision tasks and the language question answering to make the visual question answering task. And combining the image understanding with the natural language dialogue generation, we will have the task of visual dialogue. So a recent trend is to introduce the action into the vision language framework. I named this combination as a V3A circle, which requires a machine that can ask and answer questions and perform actions, all based on the visual input. The circle takes a vision-based agent as the center, and we also allow the agent to ask questions to another agent or human. We also require the agent has the ability to answer questions and queries. And at the same time, the agent needs to understand the vision agent to human conversation to perform some actions. This circle actually can be divided into different parts and lead to several different directions. For example, the ask part that is related to a topic called visual question generation, which aims to develop a model that can learn to ask high informative questions. And at the answer side, it is related to the VQA and visual dialogue. The actions that a visual-based agent can perform are quite rich. For example, referring and navigation. So it covers the topic of referring impression and language-guided visual navigation, which is a vision language navigation we will introduce today. So another version, or more precisely, an extensive version of the V3A is embodied AI, which is a field for solving AI problems for virtual robots that can move, see, speak, and interact in the virtual world and with other virtual robots. And these simulated robot solutions are then transferred to real-world robots. This requires an agent has ability of see, talk, listen, act, and reason. To see, it means it perceives the environment through vision or other sensors. And talk means it can hold a natural language dialogue grounded in their environment. And listen means it understands and reacts to audio input anywhere in a scene. And act means it can navigate and interact with their environment to accomplish goals. And finally, the reason means it can consider and plan for the long-term consequence of their actions. So this is actually very similar to the definition of our V3A. So this figure from a survey of the embodied AI summarizes the simulator and research tasks in the field of embodied AI. The VLN task is in the middle between the object navigation and the visual navigation with priors. And there are some datasets that are related to this research topic, which are CVD dataset and R2R, the room-to-room datasets. Well, the first definition of the vision and language navigation was given by our pioneer VLN work published in CVPR 2018. So in a VLN task, an embodied agent is placed at a spot in a photorealistic environment, and the agent is called to navigate to a specific spot based on given natural language instructions. Here is a typical example. For example, exit the bathroom, turn left and exit the room using the door on the left. Wait there. That's language instruction. And the agent needs to travel inside the environment to find out the target room, the target location. So here is the timeline of the VLN. The first VLN work was published in 2018. It was proposed by Peter Anderson, a PhD student of ECRV at that time, and me, who was doing a postdoc at ECRV at that time. We discussed how to use VL, the vision language, in the robotics environment, which is now a famous embodied vision problem. The first task we think of is navigation, because navigation is a more, it's a mainstream direction in the robotics. We also gave this project a name called to Bring Me a Spoon, because we think that ordering a child about 5 years old to take a spoon is a straightforward task, and instructing the robots to take a spoon through language instructions is very difficult. We quickly looked to use multiple 3D as our indoor environment and select around 90 different indoor buildings, including residences, offices. But at that time, we also had some controversies about what instruction to label. I advocated to that instruction similar to Bring Me a Spoon, which is closer to a human behavior and practical scenarios. At that same time, specific prior knowledge is required. The painter thinks that such labeling is complex for the first VLN task, and the performance cannot be guaranteed. He wants to do a room-to-room task first, only navigating to the destination room and giving more detailed instructions. It can better reflect the combination of vision language. So we started to build a simulator, use AMT to collect the data, and have the first VLN simulator called multiple 3D simulator, and the first VLN tasks and the data actually called room-to-room, which is R2R. Since then, VLN has become another essential task in the VL field following image captioning, VQA, and visual-dialog. The picture here is a roadmap of VLN. In terms of tasks and data, after R2R, there is outdoor VLN, which is a touchdown, and dialogue-based VLN, such as CVDN. And there are more fine-grained annotations, such as baby talk and fine-grained R2R, and recent RXR. and Reverie, which is an advanced version of the VLN. It is a version most close to our initial idea, the Premier Spoon. In terms of a method, there are also some variants, such as speaker follow model and the golden backbone environment dropout model, and Xinhuang self-supervised imitation learning and reinforcement learning model, which won the CAPI 2019 Best Student paper. Okay, now let's introduce some datasets and tasks in the VLN. Okay, everything starts from here, actually, the first VLN work. In this work, actually, to collect the dataset, we first build a simulator based on the multiple 3D dataset consists of more than 10,000 panoramic images. They cover 90 building scale scenes with a range of buildings, including houses, apartments, hotels, offices, and churches of varying size and complexity. We build a simulator that can travel inside the environments and receive visual information and execute agent actions. For each building, we have a navigation graph, so the agent can travel from one node to the next adjacent node. Then, the feasible trajectories are determined by a navigation graph. And we have a panoramic image at each navigable node. Given the above interactable environment and the navigation graph, we define the vision and language navigation task and propose the first room-to-room dataset. So in this task and dataset, one agent needs to navigate through the environment to find the goal location by following a natural language navigation instruction. Well, we also provide clear evaluation protocols. Say single test run only, the agent must choose when to stop and success marrow if stopped within 3 meters of the goal location. Well, there are also some other researchers proposing more evaluation metrics for this task, such as NDTW and CLS. So here is one example from dataset, and we finally sampled 7,000 shortest passes between locations in different rooms. We collected 21,000 instructions using MT and WebGL simulator interface, totally 400 people, and spent 1,600 hours annotating. Compared to the classical VQA task, the visual question answering task, VLN as active vision because the visual input is always changing during the navigation. As a sequence-to-sequence problem, the sequence in VLN are much longer at both encoder and decoder side, and we have a bigger domain gap between training and testing set. So when we start the VLN project, our longer-term target is to build a unified vision language action play center. We designed 4 levels of tasks. The first level is the room-to-room navigation, which we have introduced in the previous work. To this end, we additionally designed 3 higher-level tasks. The visible object localization task is quite like the reference expression. We need the agent to find a visible object by following a language query. And at level 3, we still want the agent to locate the object, but the object is hidden in somewhere, such as in the drawer behind the curtain, so the agent is required to perform some actions such as pull, open to find the object. So in the final level task, the human order will be non-complete and ambiguous. So the agent needs to raise a question to the human or another agent so that it can finish the task. This is more like the visual dialogue and navigation. We have seen some datasets such as HANA, CVDN are released at this level. Well, we can see the room-to-room is actually the first level, right? So, and the level 2 we formulate as a remote object reference expression task. So the agent needs to navigate to the right place and detect the target object by following a natural language instruction. For example, bring me the blue cushion from the living room, right? So the second data set I want to introduce today is an extension of VLN. So in this new task, we combine the vision, language, navigation, and reference expression. The new task is called as Reverie, standard for remote embodied visual reference expression in real indoor environments. So here is a demo of the Reverie task. So in a 3D simulator, a robot agent is initialized at a random location, then it is given a natural language instruction referring to a remote object. The agent must navigate to an appropriate location and identify the target. The agent can look up, look down, and look around at each step. The blue cylinders inside the environment actually indicate the nearby navigable viewpoints. So in this example, the instruction is go to the bathroom. In the bedroom is an orange stripe. Make sure faucet is not leaking, right? So finally, the agent need to go to the right room, find the object. In this case, is a faucet. So give us a bounding box of that target object. So the Reverie task involves both room-to-room navigation and reference expression grounding, but it has key differences from these tasks. So compared to room-to-room task, Reverie differs in two aspects. First, Reverie uses concise, high-level instruction, such as the first bedroom on level 2, while the room-to-room task takes detailed low-level instructions, such as go to the top of stairs, then turn left and walk along the hallway, right? So the instruction is very, not long, it's very detailed, right? So second, the goal of the Reverie task is to locate remote object. In contrast, the room-to-room task aims to navigate to a remote room. So there are also three main challenges. First, the appearance varies greatly even for the same object in terms of shape, scale, or aspect ratio caused by different robot poses. Some objects are even partially occluded. For example, in this example, for example, the TV, right? So at some point you can see the TV, but at some point you cannot see TV because it's being occluded by the chair. And even for the chair, sometimes we can see it, sometimes we cannot see it, and the size of it changes a lot based on different viewpoint. Second, the instruction structure is complicated, involving various linguistic phenomena such as tangling modifiers, spatial relations, and imperatives. All our instructions are collected from AMT workers other than automatic machine generated. Hence, it's more natural in our instruction. And third, instruction are with less words but more contents. On average, it's 11 words less than those of the room-to-room dataset, which means more difficult to get the target room. On the other hand, about 56% instructions mention 3 or more objects, falling into nearly 500 different categories, which means more challenging to identify the target object. So the level 3 is called the hidden object localization. So at this level, we want an agent to interact with the environment to find out objects. Although there is no such dataset at the moment, there are some similar datasets and the tasks about the interactive vision language navigation. Okay, so alpha rate is a new benchmark for connecting human language to actions, behaviors, and objects in an interactive visual environment. So planner-based expert demonstrations are compared by both high and low-level human language instructions in 120 indoor scenes in AI2Sol. So these demonstrations involve potential observability, long action horizons under specified natural language, and irreversible actions. The dataset provides both Go-level instructions and fine-grained details, step-by-step instructions. And according to the evaluation, alpha rate actually allows us to evaluate both full task and task goal condition completion. So in navigation-only tasks, one can only measure how far the agent is from the goal. But in alpha rate, we can also evaluate whether task goal conditions have been completed. For example, that whether a potato has been sliced. So the level 4 is called ask to find. So basically, we want an agent can communicate with human or other agents to help it achieve this goal. So this is related to dialogue-based vision and language navigation. So cooperative vision and language navigation, which is also known as a CVDN, is a dataset of embodied human-to-human dialogues situated in a simulator for futuristic home environments. The navigator asks questions of their partner, the oracle, who has privileged access to the best next steps the navigator should take according to a full state information shortest path planner. The dataset consists around 2,000 human-to-human navigation dialogue, comprising over 7,000 navigation trajectories across like around 80 host scans. CVDN facilitates training agents for navigation, question asking, and question answering. While in this work, they only tested on the navigation part and formulated as a navigation from dialogue history task. So the input is a ground truth dialogue history, while the output is the navigation actions. Another dialogue-based VLN is called HANA. In HANA, when the agent gets lost and becomes unable to make progress, it has the option of requesting assistance from Anna, a helper who can provide natural language and visual instructions to direct the agent towards the goal. At the test time, the agent must decide where to go and whether to request help from Anna without additional supervision. Here is an example of HANA task. So initially, the agent stands in the bedroom at A and is requested by a human requester to find a mark. The agent begins but gets lost in somewhere in the bedroom. It gets to the start location of the root green, which is B. Which is B here. To request help from Anna, upon request, Anna assigns the agent a navigation subtask described by a natural language instruction that guides the agent to a target location and an image of the view at the location. So the agent follows the language instruction and arrives at the location of C, where it observes the match between the target image and the current view. That decides to depart the green road. And after that, it resumes the main task to finding a mark. From this point, the agent gets lost one more time and has to carry Anna for another subtask that helps it follow the blue road and enter the kitchen. The agent successfully fulfills the task. It finally stops at the request object, which is the star here. So note that Anna feedback is simulated using two pre-collected language-assisted routes. Here, the green one and the blue one. Okay, so other than the 4 levels of tasks, there are some other VLN datasets. The fine-grained instructions enabled dataset is one of them. So despite the significant progress made by the recent approaches, there is a little evidence that shows that agents learn the corresponding between observations and instructions. Some researchers found that a modified self-monitoring agent could achieve similar performance with and without visual information. Among other reasons, such as dataset bias, The results actually suggest that this agent gains little information from having the two-stream information. One reason behind this is that current methods are not adequately teaching agents the relationship between perception and parts of instruction. Since datasets do not provide such information, agents can only use the ground truth trajectory as a learning signal. Moreover, given the lack of fine-grained annotation, current method cannot evaluate the grounding process at each step, as there is no ground truth signal to indicate which part of instruction has been completed. So to solve this problem, Hong et al., who is also my PhD student, enhanced the ultra dataset to acquire intermediate supervision for the agent, providing a fine-grained matching between some instructions and the agent visual perception. We argue that the granularity of the navigation task should be at the level of these sub-instructions rather than attempting to ground a specific part of the original long and complex instruction without any direct supervision or narrow navigation progress at word level. The baby walk shares the same idea by decomposing a navigation task into sub-instructions and tasks. Room across room is another recently proposed VR dataset with more fine-grained instructions. Instructions and the trajectory are actually longer in the room across room. And they also extend RxR to the RxR habitats. So in this environment, the movement continues. So another direction of the VLN is the outdoors version. The touchdown uses interactive visual navigation environment based on the Google Street View. The task is to first follow instruction to reach a goal position, and then resolving a spatial description at the goal by identifying the location in the observed image of a touchdown, a hidden teddy bear. So you are the who is the authors of this paper. So the work is another outdoor viewing task and datasets. So in this task, the aim is for two agents, a guide and a tourist, to interact with each other via natural language in order to achieve a common goal. Having the tourist navigate towards the correct location, the guide has access to a map and knows the target location, but doesn't know where the tourist is. The tourist has a 360-degree view of the world, but knows neither the target location on the map nor the way to it. The agents need to work together through communications in order to successfully solve the task. So an example is shown over here. Okay, now I will talk about the mainstream methods in the VLN. So now comes to the classical VLN method. There's actually four major categories, I think. Sequence-to-sequence model is always a good baseline. Attention mechanism is something you must try in the vision language. Some typical methods include the environment dropout and OAM, the object action aware action model. And transformer is basically all you need with the pre-trained state of art in the VLN. And classical methods include prevalent and recurrent BERT. And finally, reinforcement learning is always helpful. So like other vision and language tasks, the sequence-to-sequence model can be used as a baseline for the VLN. Here, the input sequence is the instruction and output is action sequences. One issue of the VLN is lack of training data, hence the data augmentation is actually a natural way to solve this problem. Speaker-follower model is most widely used data augmentation model in the VLN. So in this work, the speaker model random sample passes from training environments and then synthesis instructions on the sampled path with a language-generated model. So the sampled paths with the generated instruction are then combined with the original training data and assigned to a follower model, which is a general VLN model to learn the navigation strategy. So instead of argument on paths and instructions, some work arguments on the environment. The environment drop-out is a classical method in this direction. It augments new environments by modifying existing visual environments along the feature dimension. Then the new environments are sent to a speaker module to generate new passes and instructions. This method works especially well on the unseen environment splits, actually. Okay, so another type of work, attention-based framework. In ECCV 2020, we proposed an object and action-aware attention model to solve the VLN task. We know that VLN is unique in that it requires turning relatively general natural language instructions into robot agent actions on the basis of the visible environments. This requires to extract the value from two very different types of natural language information. The first is object description, for example, the table, door, and actually each presenting as a tip for the agent to determine the next action by finding the item visible in the environment. And second is the action specification. For example, go straight, turn left, this kind of words that allows the robot to directly predict the next movements without relying on visual perceptions. So in this work, we propose an object and action-aware model that processes these two different forms of natural language-based instructions separately. So this enables each process to match object-centered or action-centered instruction to their own counterpart visual perceptions and action orientation flexibly. Okay, so although the attention model can attend on different level and domain features separately, we find that the relationship among these same and its objects and direction clues are essential for the agent to interpret complex instructions and correctly perceive the environment. To capture and utilize the relationships, we propose a language and visual entity relationship graph for modeling the intermodal relationships between the text and vision and the intramodal relationships among visual entities. We then use a message parsing algorithm for propagating information between language elements and visual entities in the graph, which we then combine to determine the next action to take. Another classical way in VLN is to use reinforced learning. So one of the famous one in the actually the RCM, the reinforced cross-modal matching model from Xin Wang, who won the best student paper in CVPR 2019. So in this work, they combine the reinforced learning and the imitation learning to solve the VLN problem, achieving amazing good performance. So RL is good at solving unseen environment VLN problems because it overcomes the error accumulation issue caused by hard behavior cloning. However, RL has issues as well. At first, the reward function designed at one environment or task may not generalize well to other scenarios. Secondly, in many practical and complicated tasks, it is hard to define concrete reward functions. So in one work in our ECC 2020 work, we actually develop a so-called soft expert distillation reward to solve this issue. So our key so the intuition behind this is given while giving a certain amount of random projections information. The representation learner is required to learn the structure of this given data in the random projection space to yield a similar project distribution. The learning function is expected to predict relatively better where more expert data lays. So in this case, a strong density function is formed. It models the likelihood of the agent performing a similar action with each expert in a situation through the distillation. So this is called the soft expert distillation reward. So as the transformer becoming popular and popular, it has been used in the VLN tasks. So in CVPR 2021, we proposed a recurrent vision and language BERT for the navigation. So in our work, instead of employing large-scale datasets for pre-training, which usually actually requires thousands of GPU hours, the aim of this work is to allow the learning of VLN to adequately benefit from pre-training VLN models. Based on the previously proposed vision language BERT models, we implement a recurrent function in the original architecture to model and leverage history-dependent state representations without explicitly defining a memory buffer. Well, the secret is that we use the CLS token as a recurrent unit and use it to store and pass memory at different time steps. Our model was state-of-art on both R2R and Revry task, and we can benefit from the pre-training. For example, if we use a pre-trained prevalent model as the initialization of our model, we can achieve 63% successful accuracy, and we can achieve 57 SPL, which was a state-of-art. So we also test our model not only on R2R, we also test our model on the Revry, which requires agent to find out the final objects, and we can see our successful rate is also much higher than the previous state of art. And one benefit of this model is that it can be trained on a single GPU with only 11 gigabytes memory. Okay, so while most of existing navigation methods perform word-image matching to determine where to go next, this leads to the same image feature needs to match to different textual landmarks. Another drawback of existing method is that they ignore the directions such as left, right, front, and back, and room type such as the living room, kitchen, clues mentioned in the instructions. These clues are of great importance as they are frequently mentioned in the instruction and can be inferred from the visual perceptions. So their matching or not facilitate the agent to make correct navigation predictions. To address aforementioned problems, we propose an object in a room informed sequential transformer model. This model is composed of 3 modules: the object level initial embedding modules, the sequential transformer module, and the room and direction multitask module. So the initial embedding module takes as input an instruction, visual feature of the object, and orientation of each navigable location, so that we can match the discrete instruction word and objects in the image. So the initial embeddings are fed into the sequential transformer to adaptively fuse information from individual words and visual objects, as well as each orientation via the self-attention mechanism. The sequential transformer is able to learn the matching between visual and textual entities and has no what. The key idea of the sequential transformer is to incorporate temporal context into the initial embedding of the spatial token CLS, which will be updated according to the object tokens by self-attention mechanism in the transformer. So we actually use LSTM to maintain the memory between different time steps. And the output of the sequential transformer is also fed into the room and direction multitask module. So in this module, we can predict the room type, the next room direction, to use the room clues as a kind of training signal to train the whole model. This paper has been published in ICCV 2021. So our model achieves the best performance on the validation on scene and the test splits. Particularly, our model nearly doubles the previous best performance in terms of the main SPL and RGSPL matrix on the validation on scene. So we also note that our model ranks second on the validation scene split, indicating our model still has room to further learn from the training data. Our model also achieved the best performance on NDH and R2R dataset, which is another NDH is actually CVDN, the visual dialog navigation dataset, and R2R, which is room-to-room dataset. Note that, please note that here the compared prevalent model is actually pre-trained on the VLN dataset, while ours model are not. We just train from scratch. These results actually demonstrate the effectiveness of the proposed uniform model for these inbound navigation tasks. So here are the code and dataset for our VLN works. Welcome to check.
Okay. Thank you, Professor Wu. Now it's question time. Is anybody have questions for Professor Wu? Now I have a question. I appreciate the excellent VLN works proposed by Professor Wu. I have a question. How far is vision language navigation to applicable real-world robot that perceive natural language? For example, if we want to build a real indoor helping robot, what extra challenge we might meet?
Well, yes, thanks for the question. It's a big question. Yeah, so I think the gap is still very big. So, like in the previous talk, Drew just showed us, well, there are some work about simulation to real environment, right? So currently, nearly all the agents, all the models are trained on simulated environment. So there's still a big gap between the simulator and the real environment. Of course, the difference are quite big. So in the real environment, all the objects, some of the objects can be interactable, can be moved, right? So that's one of the biggest difference. And the second challenge, I think, between the real environment and the simulated environment is currently for the vision language navigation, most of the models and actually most of the data sets are using the discrete navigation graph, right? We have a navigation graph so the agent can move from one node to another node directly. But in the real environment, it's continuous movement. Currently we can see on the habitat or the like R2R CE and VLN and the RXR CE, the continuous environment one. It's very it's one step, but still, I think there are a lot of challenges between the simulated environment and the real environment. I think if we want to make a real one that can work in the real environment, the first thing we need to think about is how can we make a good simulator that actually can simulate the real environment very well. But I think the Happy 0.0 gave us a really good start point. Thank you.
Okay. So what extra work should we do?
So yeah, as I mentioned, I think sim to real is actually the future of the VLN. So we need to think about transfer learning. So how can we train the environment on the simulated train an agent on simulated environment, but test it on the real environment? And I think another important thing is one thing we are working on is whether we can train an agent on a discrete navigation graph, but test it on the continuous environment. So there's another kind of transfer learning. It's not sim to real, but it's like discrete to continuous. So because we know that training an agent on the continuous environment is very hard, right? So it takes you need take a lot of time of training, but you can easily train a model on the navigation graph on the discrete environment. So how can we do the transfer learning from discrete to the continuous, and how can we do the transfer learning from like a simulator to real environment? If we can do both of them, I think it give us a a good start of doing the real robot.
Okay, yes, I believe so. So due to the time limit, we should move on. So let's welcome the Professor Benzel from the University of North Carolina.
Thanks, Pengda. Hello, everyone. I'll keep it a bit short so that everyone can go to the weekend and go to sleep, etc., depending on the time zone. So let me share my screen. Yeah, can you, if I do full screen, do you see the full screen of my slide?
Yes.
Okay, great. So yeah, so today I'll be talking about video and embodied grounding for language. So there'll be two parts, as the title suggests. One will be based on how we can use video and language as basically an important medium of having our personal assistants or robots in our surroundings be able to understand the dynamic spatiotemporal information around us and do reasoning on that. And the second half will be more brief about some examples of embodied and spatial navigation plus body pose and different kinds of embodied reasonings that we are looking at. So this is kind of the motivation I was just mentioning, that for video grounded and spatial embodied natural language processing, which includes understanding and generation, an ideal such model, we are seeing a lot of these sort of personal assistants around us at home these days, right, from different companies, also including some rolling and walking ones now. So what would be the ideal future such agent? Some of the conditions that it should satisfy are basically a model that can ground on, like I said, spatio-temporal, visual, video-based environment context around it, right, for reasoning, and be able to execute and generate instructions for different kinds of tasks like navigation, assembling, exercising, and so on, right? So pretty much a collaborator and not just a task completer. So yeah, so let's dive into the first part. Like I said, this will be video-based dynamic spatial temporal grounding. So the idea here is that video, like I said, is a good medium for validating HRI research and being one of the important aspects of such research, because ideal agents or assistants around us in our homes or environments should be able to perform joint video and language understanding, right, in terms of the actual events happening around it. So the kinds of complex cross-modal reasoning that it should be able to do is be able to look at this video plus language plus dialogue information that it hears and sees, and be able to do tasks like answer questions, retrieve information, predict what could be the next event, summarize a lot of information, and so on, right? So this is why for this kind of talk, sorry, I'm getting a chat message. I'll skip that. I think that's for the previous. Yeah. So basically, this is where the sort of examples of video and language bring up make sense for HRI. So the idea is that the agent should be able to do question answering, spatial grounding, moment retrieval, also do it multilingually, and then also things like next event prediction or highlighting and saliency and summarization. So the first half of the talk, as I mentioned, will cover some of our recent efforts in the last 3 or 4 years on covering these different aspects of video and language reasoning, both through, so in this talk, I'll mostly mention the dataset efforts, but the individual projects and papers also have advanced initial models for these tasks. And then also I'll mention briefly about our recent large-scale pre-trained language models for video and language. So TVQA was the first example. In this case, the main idea was that how can we do compositional video question. So the idea would be that question in order to be answered would need the model to understand information, part of the information from the video and part of the information from the dialogue or the subtitles that are happening in the video. So this was one of the largest video question answering datasets with also 6 different video genres or categories. So things which had daily events and sitcoms, but also crime-based topics and also medical topics. And like I said, the main focus was on compositionality as well as spatio-temporal localization. So both temporal timestamps for answering the question, but also inside that, the spatial boxes inside the frames of that retrieved moment. So this is just an easy example to convey the message of compositionality. So what I mean is that the questions will be something like, what is person X holding when he is talking to person Y about swords? So part of the question, right, what is Sheldon holding is basically a visual question that comes from the video part of the dataset, whereas the when he is talking to Howard about swords is a part of the question that can be answered from the dialogue or the subtitles or the conversation happening. And there can be different combinations of this, right? It could also have combinations of first needing to do a visual localization and then go into the dialogue, right? So what was Sheldon talking about when Leonard enters the door, that kind of thing. And it could also have questions that both parts of the questions could be about just dialogue or just video. So yeah, so this is basically some from the data set. So like I said, it covers a lot of these daily activities from sitcoms of all kinds of events that happen in our daily lives, but also more complex reasoning topics of medical and crime genres. It also had a lot of different types of questions. So not just the easier like what and who questions, but also locational like where questions, when, why, how, and so on. And then it also had, in terms of size and the average length and the total length, and then also the source of the question coming from both text and video, as well as having the time annotations. It had a lot of detailed annotation. And then TVQA Plus, which was an extension at 20, was also extending this, like I said, to the spatial localization. So in case some of these question answering tasks, for example, have multiple choices, right? So the models could take shortcuts instead of having generative tasks. But this spatial localization, in addition to temporal, adds a kind of interpretability requirement, right, or explainability, where the model is not just choosing the right answer among the choices, but it also has to actually visually tell you what the temporal timestamp was, and inside those frames, what the spatial sort of localization was. And also, if you think again, connecting this back to agents at home or robots that we want to interact with, this would be also a useful information where they could be looking at all the video based surroundings, right, visual events happening around it dynamically, and be able to answer questions where, like in terms of not just the temporal localization, but in terms of spatial, it's roughly equivalent to being able to point to things, right, or gesture, but also being able to go to that part of the spatial boundary and be able to maybe pick up things or reach that location. So this would be one way of connecting pointing to a robot through video understanding. The second example is the task of text and video retrieval, moment retrieval specifically. So again, the idea here is that the model should be able to understand information both from the text and the video. So if the query is Rachel explains to her dad on the phone why she can't marry her fiance. So this, in this case, again, the blue part from the video, whereas the red part from the language dialogue component. So this has two kinds of tasks involved. BCMR is basically being given a very large video corpus of thousands of videos, and the model has to first figure out which video in this big video corpus contains that moment. And then the SVMR task, which is single video moment retrieval, basically goes into that retrieved video and localizes the moment inside that video in terms of timestamps. So there's two levels. And again, TVR was the largest moment retrieval data set at that point, with like 109K human annotated query moment pairs on 22,000 videos, and lots of other things that I'll not go into, where basically in terms of vocabulary size, it was pretty large. And then the average question, the query lengths were pretty long, and then the moments were on average shorter and more challenging to find. Then it also had question context from both video and text, and then also free, basically annotation as opposed to or highlighting things in a given paragraph. And then also it had the type of the question annotated, and so on. So there were different properties that we looked at, and also we tried to make sure that these queries have then one, usually multiple people and multiple being talked about. MTVR recently at A21, multilingual version of this. So the idea here was that, again, these models that we are developing for video-based moment retrieval should not just all be English specific. And I mean, if you think about my home or other, usually in most scenarios, right, I speak multiple languages at home. So in some sense, again, if you're connecting this to the kinds of agents that we want as personal assistants around us, they should also be able to switch between languages and understand things multilingually. So this was an example of extending TVR to multiple languages, in this case, English and Chinese, and we also presented some multilingual models that could jointly use the information across languages rather than monolingual models, with also grounding through video. Then one of the last examples of these tasks is more going into the next event prediction task for video and language. So here the idea would be that, can we build models that can anticipate some of the next events or the future events that will happen given the current premise of videos and the dialogue happening in the premise. So again, the idea would be that in this case, given a video and dialogue as premise, and a good model should be able to have higher probability for the more likely event that happens next, and lower probability for an event that wouldn't be more, in general, likely according to human common sense. So this would be an example.
Oh yeah, oh maybe a shake.
So in this case, basically the
oh yeah, oh maybe a shake
would be the examples. So these are the two things that could be possible in the future, and the green one is more likely. And there's also rationales that come with the data set that basically the woman in the white shirt pours the slush into a watermelon rind and passes it to Mark. That's the more likely event because there are hollowed out watermelon rinds as opposed to pouring it into cups. So another one would be more from a crime genre.
Got back to my apartment. That phone was on my doormat. It had a text on it.
So again, the idea here would be that Beckett takes the phone and reads the text is more likely than handing it to Dean, because again, the detective probably wouldn't hand a piece of evidence to a suspect. So these are pretty low-level common sense and sort of world knowledge kinds of requiring tasks. And the other thing that's important is that in terms of the negative examples or the distractors that were given to the task are also tricky and hard, in the sense that just a simple language model should not be able to give low probability to the wrong answers in case the distractors are very unlikely or unrelated. So this is something known as Hamlet, human and model in the loop adversarial data collection, which was a separate paper with Facebook collaborators on how to do. Basically, the idea is that you have a model in the loop when you're collecting data. And so now this has been extended to several other tasks too. The idea would be that the Turkers, the annotators, when they're giving us these distractors, they have to make sure that they can fool a pretty good state-of-the-art model. They would have to, for example, fool Roberta or GPT-2 or GPT-3 style models, so that we can make sure that just without looking at the video, a text-only very strong large-scale language model should not be able to predict the next event and differentiate from the distractors. And then the last example here is a task This is coming up at NeurIPS, so very recent, on query-based video highlighting and saliency. So this is a data set where given a language query and along, first of all, the model has to detect all the gap-based multiple moments, not just a single moment retrieval, but also more importantly, it has to also understand the saliency of the. So basically the 3 bars at the bottom of each frame, so the dashed boundaries are the relevant frames, like, and they can have gaps, right? So this one, glass is laying all over the street from broken windows beside other trash and debris in front of store buildings. So the model has to understand that this is talking about the query, then not this, so skip this. And then again, when the video comes back or the cameraman comes back to this frames, then that's part of the video, part of the query that's relevant. But also each of these retrieved moments, these are 3 annotators giving scores of how salient are these moments to the given query. So the longer bar, the taller bar, and the darker the green color is supposed to be more salient. So this is an idea where, again, if you have an agent that's looking at a lot of information around itself, not just for home personal assistant scenarios, but this has also important applications in tasks like based AI. So if you want to have, for example, a teacher should be able to take a long video in a classroom and be able to have an AI agent automatically help analyze and reduce some of the information for the teacher to look at, or even for the student to go back home and be able to, in case they miss the class or they want to repeat or revise the class, it should be able to ask queries. The student or the teacher should be able to ask queries, and the video model should be able to give all the related moments and so their saliency in terms of what was in. So this is a more recent task. Again, the paper has a lot of models. This one has a model more related to the DETR deter model and the MDETR model. So there's a strong baseline associated with this task called moment deter, which we won't have time to go into today. But also you can attend the value benchmark challenge tomorrow at the CLVL workshop, where what we did recently, this is a NeurIPS benchmark paper coming up, where the idea was that we basically took several of these question answering, captioning, retrieval data sets, including how to QA and also VATEX and Violin, and also TVQA, TVR, VLEP, so on. And this was created as a multitask benchmark where so as to promote video and language understanding models that are not trying to focus and get specialized too much in one specific task or direction, but instead promote models that can jointly do all these tasks in a uniform way. So this is a collaboration with a lot of folks working on video and language, including Microsoft, Santa Barbara, and so on. So feel free to join the challenge results at the workshop tomorrow, where I'll also be giving one of the talks on the more large-scale language models part of the video and language understanding world. So yeah, so this in this talk, I'll not be able to go into those details. So like I said, that will be part of tomorrow's talk. But here is a very brief overview of some of the recent efforts we've done on building large-scale pre-trained models for multimodality. So like I said, all the video and language understanding tasks that I've mentioned in the previous slides do come with strong baselines, but you can also get much stronger results if you start building these uniform and large-scale vision and language pre-trained models. So here are just a few examples. So LexMert and Wilbur, right? So one of those first image and language pre-training models. Then we've also done things like video plus language pre-training models. So this is December, and this is Clipboard, which is more about sparsity. And then we've also looked at things like how to use vision information to improve language-based pre-training models. So that's called vocalization, where basically BERT is not just filling the language-based as the pre-training objective function, but also it has to map to visual elements, visual mappings as part of its pre-training objective. And at NeurIPS, we have a video version of it coming up where we do video to language distillation. So how to improve language or text-only tasks that need external common sense, physical common sense, temporal common sense, and how can we improve those using information distilled from videos. And then this bottom example is an example of VLT5, where the idea is, can we treat discriminative and generative vision and language tasks uniformly as conditioned multimodal text generation. So basically the vision input, the text input, and then everything is treated as text generation, whether it's the VQA answers or the referring expression box IDs or the captions or the labels. And this way you can also handle unseen and rare answers, but also have fewer parameters. So yeah, so like I said, this one is more about video. This talk is more about video and embodied grounding, but tomorrow's talk will mention a bit more these pre-trained models. Okay, so briefly, let's go into the second part of the talk, which is on some examples of language and robotics grounding, but some of the previous talks have already given a much more detailed account of these. So in, as mentioned on the slide, in the case of embodied or virtual agents, right, which we want to have as personal assistants in our environments, again, they need to be able to have a certain set of qualities, right? One is they should be able to handle unseen scenarios. The other is they should be able to combine several outdoor, indoor kinds of tasks, such as navigation, assembling, and so on. And then they should also be able to understand body poses and movement, as well as resolve ambiguity. So these are the four sort of brief examples that I'll talk about. The first example of generalization is one of the works that we did for NACL 2019 called Environment Dropout. So the idea here is, this is the room-to-room data set that Professor Wu just talked about. So the idea would be that if you are trying to basically have a 3D environment where you're given a set of instructions and different levels of the building and different rooms, the model needs to be able to take those instructions and follow it step by step to be able to reach the destination. And the best part about this data set is that it promoted a generalization to unseen environments and rooms, right? So the whole focus is that your model should be able to do really well on unseen environments that it's not seen during training, and also sometimes during validation. So this is a big challenge, right? Still, but also there's a lot of interesting progress that's been made in the last 2-3 years. So one of these examples that we did for making progress on unseen generalization is what we call environment dropout. So the basic idea was that, can we imitate the process of having unseen rooms by creating new rooms from the given rooms? So can we create new rooms? And this was not through the the actual GAN style room change process, which is much more challenging at that point. We've been doing some of those things recently, but at that point, it was a very simple idea that, can we have new feature level rooms in terms of changing features in the current rooms in a way that there's consistency across views and across viewpoints, right? So if you move forward or backward, versus also change your angle of sight, some objects or features should not disappear and reappear randomly, right? There should be consistency across views and viewpoints. So basically at the feature dropout level, we did this to maintain these two types of consistencies. And then we generated new instructions for these new rooms, new room features, and then used the new room features as well as the generated instructions, right, in a traditional sort of speaker back translation setting, as in a semi-supervised setup, to give more information and more training data to the model. So this is sort of the basic idea. If you follow the mouse pointer, then the idea would be, you would have training environments, you would do environment dropout, like I mentioned, with view and viewpoint consistency feature dropout, take those new environment features, use the speaker model and basically different paths generated, right, to create new instructions. And then you would use this new data in a imitation and reinforcement learning setup. And this got a pretty big gain on unseen success in 2019, and was basically one of the examples among many to be able to generalize to unseen rooms in a relatively simple way. Then another example recently that has seen a lot of interesting work, including things mentioned in the previous talk, like room across room, Alfred, Reverie, touchdown. So one other example that we looked at is something we called Aramon. So the idea here was that can we have a setup where outdoor navigation is combined with an assembling task, and can we have models that can do well at how to interleave and avoid cascading errors in these two tasks. So the idea would be that there are multiple turns of navigation and assembly, one after the other. And if you make some errors, obviously in one of the earlier phases, then it should basically you will have cascading errors in phase. So the idea is that you are Aramon because it's sort of like a combination of Pokemon, which is the idea of collecting objects and arranging them is the Ara part. So again, like I said, this has multiple turns of navigation and assembling, and each turn and phase is integrated in an interweaved way. So the performance in the previous turn and phase affects the following. And importantly, we also focused on multilinguality here. So the data comes in both English and Hindi instructions. So this is a small GIF of what happens here. There's a navigation turn in English, for example, right? So you have to go across buildings and make turns, and these are different sorts of blocks from New York City using Mapbox. And then when you collect that item, you come into this sort of assembly phase where you have to set it in relation to all the other objects. Then again, you go back, you bring up other objects, and you pick up, navigate, collect those items like Pokemon. And then you're supposed to come back and assemble this with respect to the previous objects that you assembled. So this would be sort of the interweaved navigation and assembling turns. And there is also new metrics defined in the paper that basically check for these cascading errors. And this is the Hindi version of this. So yeah, so I'll skip some of the details that are in the paper. Basically, it has a diverse variety of these collectible objects. And then also there are distractors scattered in the environment to fool the model. And this creates a lot of these referring expressions and distractions. And then, like I said, from Mapbox, we have around 7 subsections of portion of New York City. And there's also a lot of different types of linguistic properties in the collected instructions. For example, egocentric spatial relations, allocentric ones. There's temporal conditioning. There's also directional reference, as well as sequencing and 3D discrete referring expressions. And then the last example that I'll talk about is something not in terms of in indoor or outdoor, but instead looking at more of body poses and having agents that can actually understand movement and like spatial knowledge, but more from the pose side as opposed to navigation. And the motivation here is, as mentioned on this slide, right? There's a growing well-being trend, which is important, and people are trying to basically have health and exercise activities such as yoga, dance, physical therapy, right? But they are also interested in being able to do this remotely. But if you want to do this remotely, which is a good way to be able to, right? You cannot have a physical therapy expert be able to come to everyone's home or be affordable. So if you do want to have sort of a human and agent in the loop kind of interaction, you do need feedback. So this was our initial efforts in having such an agent. So we call this fix my pose, where given a current and target pose, the agent should be able to generate. So let me play this again. AI 2021. So this is a current pose, which is what you are doing, and the target pose, current pose that you are supposed to be, it's the actual accurate pose that you should be doing. So the agent should be able to tell you to rotate your torso to the right, turn your head to the right, lift your left hand. So it should be able to correct your pose by giving instructions. And there's also a retrieval version of this task. And also multilinguality, like I said, it's not just in English, but also in another language, which is Hindi in this case. So yeah, like I said, this is a multilingual data set with the idea of helping us move towards AR, VR kind of glasses for correction, which can help in exercising, dancing, etc. So there's current and target, which are basically your current pose and the ideal pose, and the model has to generate these correctional descriptions or verbal guidance that can help you go from the current pose to the target pose. And there's a retrieval version of this, the evaluation easier, where given the current pose and the description, can you choose among 10 target options where 9 are tricky distractors. So this was collected in across 25 different realistic rooms with living rooms, offices, kitchens, and so on, so that there's a lot of objects scattered in these rooms. And the descriptions can have very complex referring expressions, because it might say, move your left hand so that it points remote control on top of the shelf, and so on. So it can mention a lot of these things in the surroundings. There's different realistic
Let's wait a minute.
Hello?
Hello. Yeah.
Yeah, sorry, I don't know what happened to the Zoom. I think, so I think I'm almost done. So did you see when did I cut off? Was I like not audible for a while, or was it, like, were you able to see the screen, the current one?
Yes, now we can see the screen.
No, but did I stop, did I end at this one, or did I already end at the previous one? Were you able to see
one.
this last slide?
No.
Oh, so this one, which one did you see last?
This one.
Okay. Yeah, anyway, so this one I'll skip because it's the way of how we collected data on Amazon Mechanical Turk. But like I was saying, the interesting part is how you get a lot of different linguistic properties in these descriptions, like egocentric relations, environmental descriptions like look to the bed or align your eyes with the closest lamp, but also some common sense and analogous references like extend your right arm as if you were gesturing for someone to stop, or in a golf swing motion, right? Or as if you are leaning on a cane. So different kinds of motions that we bring from external knowledge and common sense around us in the world. And like the previous speaker was mentioning, right, that sim to real is very important, obviously, as we move forward. So in this case, we also had a smaller data set on real examples of pose movement, and we were able to get a pretty reasonable and small drop going from the simulated to the real test set, which basically was a reasonable sort of promise of our fix my pose data set transferring to real images. And also these real subsets of the data contained people with different demographics and environments from what was in the simulated data set. So this is also a good way to check whether your simulated data creates specific kinds of biases or generalization issues. And then this is the last slide. So this is, I wanted to sort of end with a more simple but real end-to-end kind of example, like we were discussing, right? Can we have real sort of actions with robots in the world? So this is sort of an example more from an end-to-end perspective, starting all the way from a microphone like speech and a Connect on a Baxter style robot, giving it an instruction and going all the way from resolving the ambiguity in that instruction all the way to performing that motion using motion planners and being able to complete the task. So the idea here was, this is ICRA 2020. So the idea was pretty simple, that can we use language model based grounding and common sense to complete incomplete robotic instructions. So if I just say, pour me some water, can Baxter understand like from where to pour it and where to pour it in terms of given all the objects in front of it. So the simple idea here, like I said, was starting all the way from audio and an RGBD image, but performing common sense reasoning as a module and going all the way to motion planning. And the common sense was very basic, but effective, where the idea is you can just look at the right side. The idea would be that you basically take this sentence, which is incomplete, like pour me some water. You can do semantic parsing on this to create a frame, and you can check for what are the variables that are missing in the frame, right? So the source and the destination, and then you fill them one by one using the objects in the environment. You create sentences out of it, and you can check the perplexity of that sentence in a large scale language model. So this tells you that pouring me water from a jug to a glass is more common than pouring me water from a plate to a scissors or to to a spoon. So that's the basic idea, that you create different kinds of sentences by converting it into a frame and putting different objects in the fill in the blanks, and then get the probability of the generated sentences. So again, there's a demo that I'll not play for now, but you can check on this link. And then again, just to end with some concluding thoughts and next steps is things that we should be looking at, for example, in the next 5 years, right? So long distance understanding in videos is still an open-ended and challenging task, where we are not just looking at question answering in the range, or reasoning or retrieval in the range of 1 to 5 minutes, but what about things that happen over multiple days, a week, and so on. So longer video understanding. Also having models that could understand and new information and unseen information coming in through continual learning methods without having to lose information from the previous episodes. Bringing in other non-verbal modalities, right? So we looked at a lot of video plus images plus language plus action, but also the interplay of these with things like gesture and gaze. This is also very important in terms of bringing multiple communities together. I already mentioned the importance of non-English multilinguality in multimodal tasks, longer ambiguities and longer interactions over long duration episodes, including in the current rich simulation environments that we have. And also lastly, connecting to like HRI and RoboNLP research more to direct hardware on AR, VR, and physical assistants. Okay, great. So I'll stop there, and feel free to ask questions, but also I know it's late for some of you, so we can also, I'm happy to take questions over email. Feel free to reach out to me on this email or just basically anywhere online. And we also have postdoc positions if you're interested. Thanks.
Okay. Thanks, Professor Benso, for his impressive talk. So is anybody have questions for Professor Benso? Okay, I have one question. So Professor Benso, you do two kinds of work simultaneously. One is the tasks like TVQA, where agent observe video data from a third-person view. And also you do works on the embodied agent, which observes the data from the first-person view. So from the first-person view. So one major gap between these two tasks is the third-person or first-person view. So if we want to build a embodied agent, so what extra works we should do if we want an agent to obtain the ability to egocentric understanding?
Mm-hmm. Yeah, so I think that's a very good question. So, I mean, first of all, one easy solution to bridge the gap is that if you have an agent that basically has egocentric view, the only reason it has egocentric view is because we are using the camera that's mounted on its head. But
yeah.
We could also go into distributional video processing and multi-screen processing, where you could have also external video streams, right, that the robot is able to use. So the kinds of scenes that you're using in TVQA or some wide angle views could actually be achieved by having the agent be accessible to other kinds of video feeds, right? It could even be just like security cameras in your home. So those kinds of things are also one way to think about it, where it does not, it can be a combination of egocentric and allocentric. And then in terms of video processing data sets that are purely egocentric, yes, we have large scale data sets coming out recently on this, right? As you've probably seen in the news. So I think that will also go a long way in terms of being able to bridge the gap. But I think in some sense, when folks also work on AR, VR glasses, right, it's a lot about how wide the view angle should be, right? So to me, it's a sort of continuation of the wideness of the view. So that also is a nice continuum going from egocentric to allocentric.
So you believe that the allocentric view can help the egocentric help the training?
If it's feasible to have it available, then yes. Then I mean, basically having all. So that's a good thing for agents as opposed to humans, right? We can have models that can look at multiple views and be able to combine information, because also these different views might have strengths and different and complementary strengths, right? They will be better at basically providing different kinds of information. So that's another angle to look at.
Yes. Okay, thank you.
Thanks.
So if we don't have any questions, let's move on. So we are going to introduce the runner-up track, one of the teams that participate in the Zoom challenge.
Use our approach for human interaction for robotic navigation challenge on student dataset. Our pipeline can be divided into two parts: a navigation model as shown in the left, and a reference model that points out the target object in the panoramic view. The motivation is that we find that simply use an end-to-end navigation and detection model will result in an insufficient training in detection height. Since the detection height will be only trained in the correct endpoint in each episode, so it will be insufficient. So here we adopt the baseline model named graphic-based exploration from the original paper of Sun dataset as our navigation model, and TransVG model as our reference model. And we train them separately and combine them together in the inference stage. We also use a distance-aware strategy to make the navigator aware of the distance of the next step. For instance, in some scenario, the model predicts higher losses for point f1 than point f2. However, it also has a longer path for point f2 for point f1. So we take the distance as a normalizer for the losses and make the model tend to choose point f2 instead of f1. So in other words, we make a trade-off between the path length and the success rate of the navigator. After adjusting the hyperparameter W, the navigator will tend to choose some shorter paths with a comparable success rate. Besides, we also fine-tune some other hyperparameters like the maximal step to make the model achieve higher SPL. As for the reference model, we slightly modify the original version of TransVG to make it adaptable to the Sun tasks. The Sun tasks requires to output the height and elevation of the target from the panoramic view. We alter the output to regress the target height and elevation. We also add the orientation embedding of each viewpoint in the visual branch. Besides, there are also some other tricks. We adopt the pre-trained DTR and board weight for the visual and the linguistic branch. We also separate the target heading and elevation into several bins and predict its offset within the bins for more accurate prediction. In the end, we also performed the model ensemble strategy. Our result shows the efficiency of our method. The distance-aware strategy slightly lower down the path length with the comparable navigation success rate. And the additional reference model transfer Z lead to a better final detection success rate. Here are some references for this presentation, and thank you for watching. That's all.
Okay. Since the author is absent, we can email him if you have any questions to ask. So at last, we are going to introduce the winner team of both Soon and Reverie. This team obtains a model that significantly outperforms previous state of art on both two challenges. So let's welcome Shi Zhecheng to introduce her excellent work.
Okay, thanks for organizing this challenge. Can you see my slides now?
Yes.
Okay. Hi, everyone. My name is Shi Zhe. I'm a postdoc researcher at INRIA. I present our solution, modeling long-term history for the object-oriented villain challenges in this workshop. This is a joint work with Pierre-Louis, Macron, Cordelia, and Yvonne. Vision and language navigation is to train a navigation agent that can follow natural language instructions to navigate in unseen environments. Most of the villain works are focusing on villain with fine-grained instructions, which provide step-by-step navigation guidance. For example, turn left and continue up the stairs, go straight through the bedroom, turn right and work past the bed, wait right there in front of the mirror. The fine-grained instructions simplifies this navigation task because the agent only needs to faithfully follow the instruction and doesn't need to explore the environment. However, such instructions are cumbersome for real-life applications. A simpler way to interact with agents is to use high-level instructions, such as go to the bedroom in the second floor and clean the mirror. These high-level instructions mainly describe things and objects in the target location. So the agent has to explore the environment on its own, find the target location, and also localize the target object in the location. We call this task as the object-oriented villain task. The object-oriented villain task is different from previous navigation tasks. It poses several new challenges. Firstly, since there is no step-by-step navigation guidance, the agent needs to learn efficient exploration strategy in unseen environments. You should maintain a long-term memory of the explored themes, so the agent can more efficiently navigate to unseen areas. Furthermore, common sense knowledge is necessary for the agent to make smarter navigation decisions, such as knowing the common room arrangement. Secondly, the task requires cross-model reasoning ability to decide where to stop and which object to localize. Compared to the object goal navigation, the instructions not only identifies the room and the object types, but also contain more fine-grained attributes and the relationships to specify the exact object instance. Moreover, the object grounding is performed in panoramic images, which contain more objects and complex spatial relationships. The workshop adopts two datasets to support the object-oriented villain task, the Reverie and Soon dataset. The Reverie dataset provides annotated object grounding bounding boxes, so the agent only needs to select the target object from all annotated objects. The Soon dataset instead doesn't contain the ground truth bounding boxes, so the task requires the agent to predict the heading and elevation of the target object. The Soon instructions and navigation passes are much longer than Reverie, and the dataset and the size of the dataset is much smaller. Two types of metrics are used to evaluate the object-oriented VLAN task. The first type are the navigation metrics, which only evaluate the navigation performance. There are success rate, SR, Oracle success rate, OSR, and success rate weighted by path length, SPL. And the second type are the object grounding metrics, which consider both the navigation and object grounding performance. There are RGS, remote grounding success rate, and RGSPL. RGS weighted by the path names. The challenge used RGSPL as the primary metric because this metric considers both the navigation accuracy, object grounding accuracy, and the exploration efficiency. The state-of-the-art methods on the object-oriented VLAN task, many adopt pre-trained vision and language transformers to improve the cross-model reasoning. For example, the Scene Intuitive Agent SIA utilized the VLAN BERT pre-trained on general image caption datasets. The recurrent VLAN BERT uses the prevalent, a pre-trained navigation model on room-to-room dataset. And the recent work, AirBERT, collects images and captions from Airbnb for in-domain pre-training to improve the generalization ability. However, these works all use a condensed recurrent unit to encode the whole navigation history, which might be suboptimal to capture essential information of the environment to achieve efficient exploration. In addition, all those methods use pre-trained visual representations on the out-domain datasets, so the visual features may not be generalizable for the panoramic observations in the downstream VLAN task. To alleviate the above limitations, we first proposed a history-aware multimodal transformer for the VLAN task, called HAND for short. This work is accepted by the new release this year, and we will release the paper and code soon. The contributions of our HAND are threefold. To start, HAND is the first fully transformer-based model for VLAN task, which can efficiently encode long-horizon navigation history. Second, we propose to end-to-end train HAND, including the visual representations, by some novel proxy tasks. And finally, fine-tuning HAND with the reinforced learning in downstream VLAN task achieves state-of-the-art performance on many VLAN datasets. I'll describe the framework of HAND. For each navigation step, the HAND is fed with the text input, the instruction, the history input, a sequence of panoramic images in the previous steps, and the current observation, the panoramic image of the current step. We use separate unimodal transformers to encode each modality input. And finally, the cross-model transformer encoder takes all the modality inputs for cross-model reasoning and output contextual encodings for each input token. The main challenges in HAND is how to efficiently encode those panoramic images in the history. Assume there are K views per panorama and T steps in the history. The previous work, VLAN BERT, concatenates all objects in all panoramas, so it results in K times T tokens to encode in the transformer, which are very computational heavy. Another work, episodic transformer, instead only take one view per panorama. Though much more efficient, it cannot capture the whole history information. Therefore, in our work, we propose a hierarchical history encoder for efficient and effective history encoding. On the first level, we use a panoramic transformer to learn the spatial relationships inside each panorama and obtain a global panorama embedding. Then in the second level, we use a temporal transformer to encode temporal relationships in the history. Such hierarchical encoding significantly improves the computation efficiency without losing much history information. We end-to-end train HAND with some proxy tasks. Apart from the common vision and language proxy task, we propose two new tasks for VLAN. The first is a single step action prediction or regression. This task aims to learn how to align and text given the history for the next action prediction. The second is the spatial relationship prediction. The villain task requires more on the spatial relationship reasoning. For example, turn right, go to the back of the table. So we propose a task to predict the relative locations of two views in the observation. This is very helpful to fine-tune the visual representations. We fine-tune hands on the downstream villain task via the reinforcement learning and imitation learning. Here are the performance of hand on the Reverie and the Soon datasets. We can see that hand achieves much better SPL compared to previous works. It demonstrates that encoding long-horizon history of the environment is beneficial to improve navigation efficiency. But we also noticed that hand is limited in sufficient exploration for the object-oriented villain task. Firstly, though hand captures previous visual themes, it uses sequential representations, which make it hard to infer the house structures. And secondly, the model purely based on the model's prediction to backtrack, putting more challenges in long-term dependency modeling. And finally, the exploration can result in many redundant viewpoints in the sequence. So we further improved hand with a graphical model called GMAP for short. We built the graphical map on the fly. The GMAP enables to better encode the house structure of the explored themes. And more importantly, it allows to combine learning and planning to make the next viewpoint actions. Specifically, at each step, the agent receives the instruction, observes a panoramic image of the current viewpoint, and also has the location and connectivity information from the GPS sensor. Given the input, we have a stop policy network to predict the stop probability at the current viewpoint. If the agent decides to stop, it will select an object in the viewpoint using the object grounding head. Otherwise, the navigation policy will be applied. The navigation policy updates the graphical map and takes all unvisited nodes in the graph as input to predict the next viewpoint. It will use the shortest path planned from this map to navigate to the next viewpoint. Now we present the results. Let's first look at the Reverie dataset. Our GMAP model achieves significant improvements on the OSR metric, proving that our model can explore more areas. The large gains on the SPL also suggest that our agent can explore the environment very efficiently. The high performance of dividing SR by OSR shows the effectiveness of our stop policy, which demonstrates good generalization ability on unseen environments. But we also noticed that the object grounding is still a challenging task and requires more efforts. Next, I'll show the results on the Soon dataset. We convert the Soon task as the same setup in the Reverie, so we could apply the same model. The trend is similar to the Reverie dataset, but we notice that performance on the Soon dataset is much lower than Reverie. The reasons are threefold. Firstly, the size of the Soon dataset is much smaller, which can result in more severe overfitting in unseen environments. And second, the navigation paths are much longer and more diverse, so the navigation task is much harder. And finally, because the object annotations in the Soon dataset are very noisy, the evaluations are not quite trustworthy. Here I'll show a navigation example. The instruction is very short and high level, going to the living room and water the plant. So the agent needs first to find the living room. It leaves the bedroom and continues navigation. At this point, it is difficult for the agent at this time, it chooses to go the right direction, but in this direction, it found another visual. So it decides to backtrack to the previous viewpoints and navigate to another direction for exploration. So this time it chose the right direction and found the living room and localized the object. To conclude, in this work, we propose to model long-term navigation memory for the VLAN tasks. We first proposed the hand, which uses the sequential history and hierarchical history encoding to efficiently encode the long-term memory. And then we further improve hand with the graphical map to better explore in the environment and combine learning and planning for decision making. Our model achieved better top performance on the Zoom and Revit challenges. It achieves more than 16% relative improvements than the second place. And for our future work, we think more efforts should be put in the object grounding task in the panoramic images. That's all of my talk. Thank you.
Thank you, Shizhe, for her excellent work. So is anybody have questions to ask Shizhe? Okay, so our workshop stop here. So thank you, everyone.
Thanks. Bye.
Bye.